Welcome to the Ardupilot Developers Conference 2025, organised by KH Unmanned, hosted by 3DXR in North Yorkshire. With thanks to our sponsors, 3DXR, Aerosystems West, CUAV, CubePilot, High-Tech, Holybro, IR-Lock, KH Unmanned, Kraus Hamdani Aerospace, Maytech, Modal AI, Northwest Blue, SD Model, and Theseus.
Good morning. Did you all have a good day yesterday? Audience participation 9 o'clock, quite poor. Not surprising. Okay, just a few bits of admin from my point of view. A gentle reminder of the area. We had a fair few people going into the private residence area and a few people sort of filming it as they were going through. Please don't do that, but please keep into the conference area as shown on the map, and we're all good. There's no need for you to go there. The only reason you're going through the private residence area is entering and leaving the whole facility, in which case you should be in a vehicle at that point. Okay, the weather outlook is improving. So today we're looking pretty good. Steady state wind is fairly calm. It's just a little bit gusty, but we have no rain forecast. And originally, we had rain forecast for Sunday. That has now improved, but we are looking even windier and gustier. Again, we will just see what we can do. We might have to reshuffle some of the demos for Sunday, bring them forward a little bit. But let's see how that progresses throughout the day, and I will chat with everyone who's doing demos tomorrow. Okay. NOTAMs in airspace is very much the same as yesterday. There are no NOTAMs to affect flight ops today. Our NOTAM is still in place. And as it's the weekend, the probability of low-flying military aircraft is even lower, but please still remain vigilant. And if you do hear anything, just say to anybody on the flight line that if you're nearby. The day plan. We've got an incredibly busy day today. I'm afraid I'm going to have to be quite strict on timings, which is a shame, but because I want everybody to be able to do their talk to the best of their ability and show off their stuff, but we need to be fair to everybody to get through the day. We've got the conference dinner after the actual event today. Everybody will be getting onto the buses. The buses are going to take everybody to Richmond Centre. Then we've got the dinner, and make sure to stay for the evening. We've got a special surprise for everybody that we want everyone to see. So please do stay around after the dinner. And then after our little surprise, we're then putting on buses to take everybody to back to Catterick Garrison, to the Holiday Inn and the Travel Lodge and Scotch Corner. Everyone else will already be in Richmond to go back to their hotels. A few general points. We do have a roving mic. Audience members that are asking questions, please put your hand up, make yourself known, and wait for the mic to get to you. Speakers, if you find that the person asking the question has not waited, please repeat the question so that it is heard on the live stream and so that make sure the rest of the audience here can hear it. Separate point now. Having chatted with everybody, it's become very clear that there are many members of the developer team who are using really ancient hardware, and that's not really a way in which we should be developing moving forward. So if any devs need any hardware, please see James. James, give us a wave. Everyone knows James. Please go and see him, and we will arrange to get you some new hardware to move forward with. Finally, there are a number of requests to go to the Darlington train station tomorrow after. So the question is, who's the we and we will get you hardware? The we is the project, Ardupilot project. Speak to James if you want more details. So a bus for Darlington Station tomorrow. We're going to set one off to take people straight from the conference to the station. If you do want to be on that bus, please come and speak to a member of staff so that we can add your name to that list. Ryan. Okay, so the question is the bus going to go straight from the conference venue? Yes, it is. If you have luggage that you need to take, can you bring it with you to the conference venue? Because we will be going to the train station direct from here. Good question, thank you. Any further questions? Super. Randy, if you want to come and set up, and then we've got a little bit of time, we'll get started shortly. Thank you.
We will shortly be resuming APDC 2025.
Okay, ladies and gentlemen, let's start our first talk. We've got Randy Mackay and Willian Galvani with the small aerial photography drones with AP.
Okay, good morning, good morning. My name is Randy Mackay, and I am the release manager for Copter and Rover. And yes, this is a two-part presentation, so I'll be doing, at the beginning, I'll be doing a little review of my aerial photography copter, and then I'll hand over to Willian, who will talk more about BlueOS. But before we get into it, I just want to say thanks again to Matt and Peter Hall and 3DXR for hosting this great event, and also to our partners for supporting the conference. Okay, so you might ask, why bother making another aerial photography copter? There's lots of them out there, right? But I'm often asked, where can I buy an RTF copter? And there are many options, but I think what the person asking the question actually wants, or is actually asking, is where can I buy an Ardupilot based drone, which is like a Mavic? And so that it comes with a whole bunch of extra conditions. They want an aerial photography copter, which can record like 4K video. They want real-time video to the ground station. They want it to be easy to fly. Not too complicated, at least 30 minutes of flight time. They want a smart battery. They want some kind of object avoidance. They want some kind of cloud integration, maybe automatically uploading files to the cloud, maybe automatic installation of new firmware. And they also want it to be not too scary looking and not too expensive. So once you add in all those conditions, it's actually a really tall order. It's not easy at all. And so I thought that, I've been asked this question for so many years, and I thought this year I'm going to try some of these really hard things that have been hanging around for a really long time. So I thought I would try and make one, and successful or not, at least I will highlight those issues that we need to improve upon. And make it easier for the next person. So this is the hardware I chose. I used a Cube Orange Plus and a Here 4 GPS. Also, I wanted this copter to be use as much of the new technology as we have available in the Ardupilot community. So I wanted it to be Ethernet based. I want the camera, the autopilot, everything else connected via Ethernet if possible. So I used a Cube node to allow the Cube Orange Plus to be able to speak Ethernet. Also, I wanted a companion computer, so I put, it has an RPI compute module 4 or 5, either one. I'm using AM32 ESCs. So you remember Tridge demonstrated this for the first time, I think, last year at the conference. So it's got those. I used the BIM drones design. So Huibin is right there. He helped me a lot. On his website, he's got an open source AM32 development board, so I use that as the base for my ESCs. We've also got a Quectel LTE modem. The drone can also support HearLink, but in this particular variety, it uses a Quectel modem. The really cool thing about these modems is that there's like 12 different versions you can buy. So I've got the Japanese one normally, but for this conference, I wanted a DigiKey. I ordered a UK version. It totally fits in the drone, and it works. It worked in like 30 minutes. I couldn't believe it. Then it's got an XF Robot Z1 mini camera gimbal on the front. Sorry, I should turn it around. And the reason I chose this one is because it's the smallest Ethernet-enabled 3-axis gimbal, camera gimbal that I could find. So that's why I chose that. It's got a HereFlow optical flow sensor on the bottom here for low altitude non-GPS. It's got 2 Benewaki LiDARs, so it's got a downward-facing one, the TF20L, and then it's got a forward-facing TF Nova. And the reason I chose that, the Nova, is because it's actually got a 14-degree field of view. So for forward avoidance, you know, better chance of seeing the person or whatever. I use the T-Motors 400 kV motors. It's a 6S, it has a 6S battery. So the 400 kV motors, MAD 12-inch folding props. And then on the bottom, it fits a Foxtech semi-solid state battery. So semi-solid state batteries, I love them. You know, they're slightly more expensive, but you get more flight time. So if you're competing with, I don't know, some other mass market drone, that's an easy way to get more flight time. Then also, I think what's also quite cool, it's still a work in progress, but a BMS, so a smart battery. This one is also from Vim Drones, and it's got a little, it will eventually be integrated into the battery. That's not done yet, but it's got a little button, and you push the button, and you can see the charge of the battery. So right now, this drone uses XT90s, because that's what the battery comes with, but we're hoping in the future to replace it with a custom battery which has the BMS inside of it, and also easy to connect and disconnect pins. So that's in the works. Oh, also the frame itself. This was designed by Tsuyoshi Arakawa, who works at my company, Japan Drones. And yeah, it's made of 2 types of, it's 3D printed. The bottom is PA12W nylon. Oh, sorry, ASA carbon fiber on the bottom, printed with a bamboo printer. And then the top part we ordered from a professional company. It's PA12W nylon. That's, you know, so it's a little bit prettier on the top. It's nice and smooth. Better than our printer could make. So that's what I've put in there. I'm happy to take questions at any time, by the way. Okay, so I'll get into the hardware a little bit more on a future slide, but before I do that, just want to show that it actually flies. So this is its first test flight about a week and a half ago in my garden, and this is the stock Ardupilot tune because it is a very standard size vehicle. Now, it's a 450 size vehicle. Totally flies. It's hard to see, but the vibration levels are very low. The EKF is very happy. There's a little bit of barometer interference when the vehicle takes off, probably because we have a fan on the front. We have a cooling fan, and maybe the thrust from the propellers goes into the fan and causes a little bit of interference, but it's actually about 3 or 4 meters of interference, but it's very transitory. EKF just gobbles it up, so it's no problem. So, totally flies. Okay, so now, I think what's really special about this drone is the custom carrier board. So, we had an earlier version of the drone, and we put all the different parts, just regular parts you could buy off the shelf into it, like a drone net, a cube orange on a small carrier board, etc. And it flew really badly. And the big change was when we added this custom carrier board. So I developed this with a company called Running Electronics in Japan, and it's got all the parts that I talked about earlier. The pins are in the perfect place, so that previously it was a mess. I don't have a picture, but the wiring was a mess in the earlier version. With the custom carrier board, all the wires are right near the components that they're connecting to, so you open it up, and it's very nice inside. Also, though, the carrier board really improves the rigidity of the frame, so the vibration levels drop down to very good levels, and it flies much better. Also, these mass market drones, the reason that they're so cheap is because you can manufacture a whole ton of them and it's really easy to manufacture them. So having a carrier board in there makes the assembly and the build much faster and much easier, and therefore much cheaper. It also saves on weight and cost, I believe, because you're not paying a profit margin to every single component manufacturer. Instead, suddenly you are the manufacturer of many of the parts. So like the ESCs, the switch, et cetera, all of those things are suddenly manufactured in Japan locally. So, sure. Another nice thing about the custom carrier board, we put all the hot components on the bottom. So the ESC and the cube node and the Raspberry Pi in particular, those all get very hot. So we put that on the bottom, the autopilot's on the top, and the fan blows over the bottom only. So it doesn't affect the barometer, but it keeps all those other components cool. And so there's a little fan controller right on the front here. Oops, sorry. Little fan controller. It turns on and off the fan. Right now it's manual, but I'll add a Lua script, so when the components get hot, it automatically turns on or off. So that's that. Cool. Okay. Any questions? Yes, Jonathan. Oh, wait, sorry. Let's wait for the microphone. Where's the microphone? I'll take a drink.
Citation needed on doesn't affect the barometer.
Sorry, you mean the fan?
The fan.
Yeah, well, as far as I can tell, it doesn't affect the fan.
Okay.
Okay. Sorry, I don't get it. I'm sorry. Was there another question? I think I saw somebody had their hand up. No? Okay. All right, I'll move on, if that's okay. Okay, yeah, so then that was the hardware. Next, for the software. One of the things that I mentioned back on the earlier slides about, people's expectations, they expect OTA updates. And so as much as possible, I wanted to be able to update every single component on the drone. So, so this is the software stack I chose. For the ESCs, AM32 ESCs connected via drone CAN. So again, you can update the software without any problems. We also have we have feedback from the ESCs, current voltage, everything, RPM. We can tell when a motor has failed. So yeah, that's why I chose that. Ardupilot in the middle. And that includes, of course, regular Ardupilot 4.7, but then, many of the other components, the cube node, the here4 are all AP perif. So yeah, Ardupilot in multiple places on the drone. And then at the top level was BlueOS. And this is one of the parts that I'm most excited about. I obviously saw William's presentation last year about BlueOS. I needed something for the companion computer, so I gave it a try, and I'm really excited about this part. And for me, I'll talk about it a little bit later on later slides, but what's really exciting for me is that suddenly it's like walking into a new room. We have a whole new computer that we can play with. There's all kinds of extensions that we can write that we just could not put on the flight controller. The BlueOS had, well, I should talk about it on the next slide, actually. But there's just so many things that we can do with BlueOS, which I'll get into later. So I'm really excited about that. Here we are. It's right here. Okay. So why is BlueOS a great choice? It already exists. You don't have to make it yourself. It's got a development team behind it, Willian and the other guys, supported by Blue Robotics, right? Has a real business model there. It's got a large user community already who is helping with beta testing. It supports Ardupilot. Previously it was just subs and boats, but now it can, it's getting better at doing multi-copters. But the next part is the extensions, which I love. So with extensions, which are based on Docker, you can very easily take like any Python program or whatever that you've ever written, and you can roll it out on BlueOS. And you also get access to an interface. So this is my optical flow extension that I wrote in a couple of days with help from Sanket Sharma. Where's Sanket? There he is, right there. So he's one of our non-GPS experts. So he helped me with this extension. But there's a bunch of extra settings that I wanted to put in the extension, like what image quality should I use? What's the maximum number of points that I should use for the optical flow? You know, anyway, there's a bunch of configuration that I wanted the user to be able to fiddle with. And with BlueOS, you can do that. Your extension can have a front end, and you can put all the little settings, et cetera, in there to make it easy for the user. Also, BlueOS has easy access to Mavlink from the ground station or the autopilot. And it also has easy access to the camera. So, for example, if you wanted to write a BlueOS extension, which took images from the camera, I don't know what you want to do, maybe you want to identify what's in the image or something, you should have a peek at my precision landing and my optical flow extensions, because they do that. They can grab frames at 30 hertz, and you can do whatever you want to do with them. Also, the programming has become so much easier with thanks to Claude AI and other AIs. I'm mostly a C++ developer. I have not done very much Python or JavaScript, almost zero JavaScript. But even so, I could put together extensions in 2 or 3 days. And just the last thing is just getting back to the OTAs. So BlueOS has built into it OTA support. So when a new version of BlueOS is available, and you log in, you pull up the web page, it pops up a little message saying, a new version's available. Do you want to upgrade? And you say yes, and it installs the new version. And the extensions are not quite so, they don't have a little pop-up unless you add it yourself, but it is still quite easy. You can go into the extensions screen, you can find your extension and just, pull a drop down and say install, and it'll install the latest version. So it's quite easy to do all that, software management or release management. Any questions? No? Cool. So, how does my copter use BlueOS? I've already talked about it a bit, but it uses it in a number of ways. The first one is the LTE telemetry. So, like I said, this drone can take a HERE link, but this particular version uses LTE only for the telemetry. So BlueOS has a zero-tier extension, which makes it easy to connect to your drone from your PC. It's got this high-altitude optical flow extension. So previously for optical flow, we've always had a camera which is fixed to the bottom of the drone, and I'll talk about it on a later slide. But with BlueOS, you have easy access to the aerial photography camera. You can get images off of that easily, so I use that for optical flow. Similarly, precision landing. I've seen a lot of implementations out there of precision landing using April tags. So I built another one, fully open source, of course, which also uses the downward-facing camera gimbal. Automatic image and video upload to the cloud. I've also got another extension for that. And by the way, all these links on my slides here, I'll provide the slides afterwards, but you can go and have a look at the code that I've written there and steal it if you like. So coming soon, robust live video. So live video does work in BlueOS. It's not completely stable in my opinion. So I've been working with the BlueOS team to improve that. But yeah, it should be ready quite soon, and we will show off what we've got later today. I'd also like to be able to upload logs to the cloud, so that after you do a flight, they go up into the cloud, so you've got a permanent record. Visual follow me. We've actually got quite a backlog of Python scripts that have been written over the years, especially by GSOC students. So Asif Khan wrote a visual follow me Python script for one of his projects, one of his summer projects. So I'm aiming to turn that into a BlueOS extension as well. And finally, NVIDIA Orin support. So sometimes if you want to do really, everybody knows it, right? A Raspberry Pi is not bad at image processing, but sometimes you need something more powerful, so an NVIDIA support would be great. Okay, cool. So I'm just going to dive in a little bit more deeply into the high altitude optical flow feature that I added. So normally, when we do optical flow, we use a downward-facing LiDAR and a small optical flow sensor like the here flow, which is directly connected to the frame of the vehicle. But you know, and I think this is a great example of where we can do it better with BVLOS and a aerial photography camera. Because the regular optical flow sensor is fixed to the body of the frame or of the drone, it means that you know, as the frame rotates, you know, it's generating all kinds of flow sensor values, right? And we have to be very careful to subtract those. So we have to look at the rotation of the vehicle, estimate how much flow we would, you know, what flow values we would get based on that rotation, and we have to subtract that from the optical flow sensor values. And the timing has to be very, very precise. And as the vehicle goes higher and higher, you know, that the movement, the actual movement of the vehicle, because as it gets further away from the ground, the actual movement of the vehicle becomes a very small number. And so that basically it limits how high we can use optical flow, because there's basically so much noise coming from the movement of the vehicle. So yeah, being able to use a very high quality image from the aerial photography camera, and also, you know, because the camera gimbal is on a gimbal, all that noise goes away. Suddenly, optical flow works at a much higher altitude than it did previously. In my tests, the limits have always been more like, you know, 20 to 30 meters maximum. But you know, with this setup, I've already achieved 100 meters, and maybe even higher is possible. So, also, one last point I didn't make was that because we have a more powerful CPU in the form of the Raspberry Pi CPU, that's much more powerful than the little you know, optical flow sensor, so it can use more points. And also, we have full control over the algorithm. So, you know, optical flow normally doesn't work perhaps if the vehicle is yawing a lot. You know, we can enhance the algorithm to work better. So here's a little video taken in my hometown. It's quite a simple video, but this is all non-GPS. The GPS is not on for any part of this flight. And I created a mission. It flies first to 20 meters, and it flies forward about 60 or 70 meters and climbs 100 meters. This is all in auto mode. Up it goes, up it goes. I mean, basically nothing goes wrong. It does the whole flight using only optical flow. There is some drift. It goes out of the range of the LiDAR. So we've enhanced the EKF a little bit so that when it goes out of the range of the LiDAR, it will fall back to using the terrain database. So there's a little, that's not 100% accurate. Also, it's just a flow, you know, the flow algorithm itself just leads to drift. There's no absolute position from it. Yes, Tim? What's the range of the LiDAR? Sorry, okay, yeah, so the question is, what's the range of the LiDAR? I am using, what is it, the TF20L, which is about 20 meters, maybe 22 meters. So it's well out of the range. There is some drift. So if you look closely, you can see down here, the drone thinks that it's about here when it's actually here. So, you know, we are getting, you know, 5 to 10 meters of drift over this 2-meter flight. But if you look really closely, you actually see that most of that drift occurs during the takeoff. So immediately after takeoff, you can see it moves on the map. And that's probably because, you know, at very low altitudes, any kind of error turns into quite a large drift. So, you know, I think if we only activated the optical flow when it was high up, it would actually drift a lot less. And I'm hoping to show that in a demo later. Okay, I think I'm a little low on time. So yeah, if you're interested in getting involved, there's a couple of ways you could help us all out. I am at the point where I've built this pretty good frame, I think, and I'm considering about how I could produce at least 200 of them. So, any advice you have on, frame materials, design, motors, propellers, whatever, companion computers, I'd really appreciate feedback at all. If you're a core developer at Ardupilot, I'd love to send you one. Only ask for it if you're really going to use it, though. If you're a hardware manufacturer, especially a camera gimbal manufacturer, we really need small camera gimbals. If you look at a DJI, their camera gimbals are tiny and fantastic. We'd really like smaller camera gimbals. And also, would really like to be able to control the image quality and the frame rate more. So this, a lot of these camera gimbals give you some control, but they're basically built for use with a HearLink or a similar system. They don't let you reduce the frame rate to really low value. So a little more control would be nice. Is there another question from Tim?
Very nice product, Randy. Hey, just wondering, how fast can that drone fly?
I don't know. It has only flown for less than 5 minutes. So we're gonna double the flight time during this conference, I hope.
Let's test that out there. I'm really interested. Can it keep up with a plane?
I don't know. Maybe. I don't know.
Maybe? Okay.
I mean, I guess it should be able to do 20 meters per second, but I really don't know. I'm just pulling that out of the air. Okay, also if you are an autopilot manufacturer, more Ethernet-enabled autopilots, please. We've got a few, but more would be better. If you're a software developer or a beta tester, if you could please consider trying BlueOS. Maybe make an extension of your own. I've got some links here to some great BlueOS documentation which shows how to build an extension. Also, of course, please feel free to steal my extension and use it as the base for your development. I also think, though, that BlueOS would benefit from just having more people test it out and then report issues. Maybe you can fix those issues yourself. It's all open source. Maybe you just report them. But let's have a run at BlueOS and try and uncover every issue we can and make it really, really robust. If you're like a drone service provider, maybe consider adopting this hardware and software stack. I think the more people use sort of consolidated or similar hardware and software setups, the more we can sort of share and reduce our development efforts. Okay, that's it. I just want to finally thank a bunch of people who helped me out. A ton of people helped me out. So Huibin helped me out over and over again with the ESCs and the BMS. William here, of course, helped me with BlueOS. Sanket for the optical flow. Sid helped me out a ton with the Cube node, and also my main sponsor, Eames, who lets me work on all these cool projects. QPilot, of course. Drone Japan, who did a presentation. They run the drone school. They were actually the inspiration, I think, for this project. Running Electronics, who did the carrier board, and then Foxtex and FX Robot, they gave me free hardware, so thank you very much. And now I will, if there's no more questions, sorry, one from Ryan.
Yeah, I was just curious, as far as using the imagery data on the companion computer, what do you see would be useful for most people buying this kind of vehicle, as far as capabilities?
Sorry, I couldn't quite hear that, actually.
What capability would you plan to add on the companion computer to use the imagery data that would be most beneficial, you think, given your experience with the users?
Well, I mean, I guess it's a middle market aerial photography copter. So most people just want to have, take videos, take pictures, and have them readily available, as soon as they land. So I think we already have that to some extent, but making that really smooth, supporting lots of different cloud services. So for example, Google Cloud or, I don't know, some other picture server that's already available. I think adding support for that would be really great.
Thank you.
Is there any question here?
Thanks for the interesting talk. You talked about OTA updates for the computer itself, the BlueOS. Have you got as far as doing OTA updates for the Cube and for the peripherals?
Cool. Yeah, thanks very much for asking. Yeah, so you might, people who follow my YouTube channel very closely might have noticed that about 6 months ago, I did a video showing how to update the cube's firmware from the SD card. So we should already be able to make an extension in BlueOS that just forwards, that goes off to the Ardupilot server, grabs a bin file, MAV FTPs that over to the SD card of the cube, and then reboots the cube, and that should update the firmware. So it should already be possible, it's just a little bit of programming. I think we actually should make an extension which handles all of the hardware on the drone in one page. So, you push a button, or maybe you don't push any button. Maybe you push one button, and then it goes through and makes sure that your AM32 ESCs are updated, Cube is updated, BlueOS is updated, all your extensions are updated. Make it really easy.
Thank you.
Just one in the middle there.
Would you want to limit how much customization you can do with it if you were giving it to other people, or would you lock down to them only being able to change a few things?
Great question. Yes. So how much should we lock down the drone? I think it's a balance, and you probably want to make it maybe it really depends on your use case. I've got an item on my to-do list to make another video showing people how to lock down all the parameters in Ardupilot, because Peter Barker has done some great work with a Lua script, which allows you to very carefully and precisely lock down just some parameters and not others. So I'd like to incorporate that somehow, but haven't quite got there yet. How are we doing on time?
Half an hour in.
Half an hour in. Okay, so we can do one more. Can we do Eric at the back there from Modal AI?
Thanks, Randy. Just wondering on the high altitude optic flow, is that the same camera that's also doing your main video, or do you have a separate camera that's doing on a gimbal specifically for that? And sort of a related question, is the downward facing LiDAR also on the gimbal, or is that just mounted directly on the frame?
So, okay, yeah, thanks. So it just uses the regular aerial photography camera for the high altitude optical flow. So no extra weight, just a little bit of extra programming, a little bit of extra software, that's all. And yeah, for the LiDAR, it's got the downward facing LiDAR, but that's only 20 meters. So beyond that, it uses the terrain database. It's built into Ardupilot. So yeah, it just falls back to the terrain. Does that answer your question?
Yeah.
Okay, and just one last one right here.
You mentioned you suffered a little bit with the live video,
yes.
Frame rate, resolution. Can you talk about all the pain points?
I think the BlueOS guys know better. I think there's just a lot of different. I don't know. I think William, you should answer.
Okay, so the question is about why changing resolution and bitrate. Is that it?
I think it's just why was live video so difficult? Why is live video so difficult to get working?
I think the main issue is the actual bandwidth we have available. The available bandwidth can change if you're using, let's say, a HearLink or an LTE modem. And if you don't have control over it, you just can't get the whole video through the link. And then you start losing packets and the video freezes.
On the RPi, what did you use? How did you handle it?
Yeah, we don't have quite a good solution yet. So that's why we are looking for cameras that allow actually controlling the bitrate. In BlueOS, we use Cockpit. Cockpit uses WebRTC. WebRTC is a technology that has the infrastructure to do bitrate adjustments in real time to fit the available bandwidth. But it's not convenient to do it on a Raspberry Pi, for example, because you have higher latency and a lot of CPU usage. Exactly. The Raspberry Pi 5, for example, doesn't actually have a hardware encoder, so it has to do it on the CPU.
But it's also just wasteful, right? It's wasteful to basically take the output of the camera, downsample it or whatever you want to say, reduce the resolution, reduce the frame rate, and then send it along. The camera had to encode it all itself. So you're basically doing it twice. So you're adding lag, And one of the things that people get upset about is lag in your video, right? Get the cameras to do it, you know, as we need it, right from the beginning. It would just be so much better. So I think at this point I should hand over to Willian.
Yeah. Sounds good. Okay, so I'll just give you a BVLOS update since last year. I am Willian Galvani. I am a software engineer with Blue Robotics and the Ardusub maintainer. So I'll start with a quick refresher, just why we started working on BVLOS, what were our goals, and maybe do a demo, if the demo gods allow me. Then I'll tell you what's new, what we're currently working on, and what are our future plans. And then you can try it yourself as well. So why? Originally, we had a companion software that was forked from Ardupilot's companion a while ago. It was started in 2015. It was based on Node, it was a monolithic project, and it was designed for a single application, which was our Blue ROV. An integrator's ecosystem was not a thought at the time at all. And it was deployed as a Raspberry Pi image, and the updates were basically Git pulls. So it was pretty bare bones. So that resulted in some flaky software updates. It was difficult to support more accessories. If an integrator wanted to change the code, they had to fork, and then that broke the updates through Git because it could cause conflicts, and basically the integrator had to keep their fork up to date. Being a monolith, the development was also hard, and performance of some services was also not great. And you basically could do no customizations there unless you forked and everything else. So what were we looking for? We wanted something highly modular and extensible. That was critical. We wanted easy and reliable software updates. We wanted a web-based dynamic UI, and we wanted to build it with modern technologies. We wanted to support any Mavlink vehicle, and our initial target was the Raspberry Pi, but we always kept in mind we wanted to support additional hardware. So BVLOS is our answer to all these things. It's basically an embedded ecosystem that we built on top of Linux. So in order to achieve the modular, easy to update, and extensible system, we picked Docker. We have two base containers. We have our core, which has all the services in it and has the basic functionality. And then we have Bootstrap, which is a startup / watchdog system. If it notices anything is wrong in core, it reverts it to a non-good version. So it's hard to actually break the system. We were looking for a low entry barrier and learning curve. So most of our services are quite isolated. So it should be easy to look at their code and understand what's going on. Most of them are written in Python using Fast API, and that also gives you Swagger API with all endpoints well described. You can easily play with the APIs and understand what's going on. We wanted to keep it compatible with as many services as possible, so we needed Mavlink communication. The Docker images, they help integrating everything. In order to resolve the performance issues, some of our critical and our performance sensitives are now written in Rust. That includes now Mavlink server, which is our router-ish. Ish because it works mostly like Mav P2P. There's no actual routing in there. Camera manager is also all Rust due to, again, performances. And that leaves us some red room for user extensions and other functionality. On the customization part, it's quite easy for integrators to extend the system. We allow a range of UI changes. You can just add your own CSS easily by dropping files in the right places. So no change required at all. The vehicle 3D models are also just dropped in the right place. So in order to work with it, you can basically just fork it. The infrastructure you need is just a Docker Hub account, and a GitHub account would be helpful too. Once you fork it, BVLOS will start fetching updates from your fork, but you can easily switch between both of them just by typing down on the UI your remote URL. I have a feeling that the demo might not work. Nope. I failed. Echo? Okay, let's leave it for the end. So what's new? Since the last year, we had 647 commits, including 31 releases in beta plus stable. We worked a lot on expanding hardware support and fixing bugs. We're also working a lot on networking support. Right now, we do support 2 network backends. That's Network Manager, and then just, what's the other one? Yeah, we're trying to support multiple host systems. That means we have to interface with the underlying network manager. And we are also making the extension system more versatile. So what's new? On camera and video, we now support H.265 video. That should work easily on Q-ground control. We also support it on WebRTC, but the browser support on WebRTC is spotty. If I recall correctly, Safari is the only one that actually supports H.265 on WebRTC. We have additional camera configuration and gimbal setup on BVLOS, better UIs to doing that. And Mavlink Camera Manager is being heavily worked on to support additional features. We recently got OnVIF support there for automatic video stream discovery, and it can also now configure the video streams using the OnVIF interface. So we can change brightness and all these little things. Another interesting thing, we're working a bit on safety, so now BVLOS lets you know if the vehicle is armed. It warns you if what you're trying to do is dangerous. You can still go through, but we are warning you that you probably shouldn't. This is a new interface for setting up the gimbals. Right now it's mostly for servo gimbals, but we want to keep on expanding it. Our compass setup / diagnostics view now includes more data sources, so it can now show you the GPS heading as well. So here you can see the heading from each individual compass plus the EKF plus the GPS heading. We are slowly filling up the vehicle frames in 3D. Copters are going soon, but there are so many copter frames, it's not quite as fun to do. We have a new helper for setting the HRS orientation, so you can visually see what it looks like, because we all know that enum is not very helpful. On network connectivity, we now can show you if each interface has an internet access. The green globe means it has internet access. If you have multiple interfaces with internet access, you can change the priority by just dragging them up and down. So if you have a backup for G-Link, you can just move it down, and it will only be used if your primary is not available. We now have an API for setting up the IP routes as well, if you need. And we now use a backup DHCP server by default. So if your Pi doesn't get a dynamic IP through DHCP, it will just start its own. So if you have IP cameras and other things connected, they can still get an IP. And I guess the most important for this talk, we got Ethernet-based flight controller support on Randy's request. On Mavlink routing, we are now using Mavlink server. It has been heavily worked on recently by our Rust engineers. It's insanely efficient, very fast, and it has a great diagnostics interface. You can plot basically any data you see. You have a list of all the vehicles and components, and it supports all the regular Mavlink endpoints. I mean, Mavlink protocols. Well, transports, like UDP, TCP, serial, and WebSocket. The WebSocket API is right now compatible with Mavlink to REST. I don't think we have a raw Mavlink over WebSocket yet. We have been working also on the extensions ecosystem. It's growing. Randy wrote two new ones. I myself have been playing with visual odometry and what's the other one?
The OD cameras, right?
Yeah, I'm working on integrating visual odometry with OKD cameras, which is fun. We now also have some new extra fields in the registration API, and so you can just add additional data there, and we are using that to expose widgets to cockpit or actions to cockpit. So in this example, for example, we have a sonar extension that exposes a sonar widget to cockpit. So you can, when you open cockpit, the widget's there. You have a note, hey, I found this, and then you can just add it to the UI, and you have your sonar integrated with cockpit. Same thing you could do with camera actions on a camera extension, so you can just have camera controls being exposed to cockpit. And more, we are working on a new dashboard UI on the homepage, so you have a digital twin there. This is still very initial phase. We're going to work on it a lot more. We have been working heavily on bug fixes, so please report everything weird you see. And we are also working on supporting basically all of the serial boards on Ardupilot. Okay, so what's coming next? We are working hardly on integrating Xeno there. Xeno is a pub-sub communication bus. I think ROS 2 is moving to it, right, Ryan? This is interesting because it allows you to have a synchronized log with all services and video and Ardupilot data. So you can basically have a snapshot of the whole system at a given time if anything goes wrong. We are also looking forward to migrating our front ends to using Xeno because right now we rely a lot on HTTP requests, which could not be the most efficient transport media. We already have on the front end, we can show the Xeno network. So you can see all the services there, and if there's a computer connected, you can also see our computer connected, everything in the network will show here. Another thing we're working on is MCAP. So all this Xeno communication will be stored into a MCAP file, which is what I said on the previous slide. This is how we can replay and understand the whole system at once, at a given timestamp. We have been working on ROS integration. I guess I myself personally I haven't been very friendly with ROS, but I'm giving it a chance now that I managed to Dockerize it. So that's another place where the BVLOS extension system helps a lot. Another exciting thing is we're working on Foxglove integration. Foxglove is a very nice application to visualizing data.
Sorry, quick question back to the previous slide. And maybe I should know, and hopefully it helps other people. I don't know what MCAP is.
Oh. Do any of you two want to answer? Because they will have a more complete answer.
If you've used ROSBAG, it's a better format than ROSBAG where it includes your message definitions. It's essentially like a bin log, but it works with large amount of data, including like LiDAR and camera data.
Yeah, but now you have to answer what's a ROSBAG.
Well, it's like an Ardupilot bin log, but for large amounts of data. It's very efficient for, you know, if you're collecting a gigabyte every minute, and to be able to search data and run transforms on that.
Yeah, it's basically a ROS standard for logging data. Okay. Oh yeah, and here we will include the videos, so we can replay the videos also with everything. In Foxglove, you can have the whole vehicle attitude. Well, the map's not as easy because we don't have enough resolution, but if you have a LiDAR. Other things we're working on, well, we are planning on. We need better resource management and tracking, including CPU usage, memory usage, I/O. And after that, using that, we want to make a better notification system so we can actually let users know if anything is, let's say, out of bounds, anything unexpected is happening. And that will also include online backend so we can notify of critical updates, version changes, and safety issues. Okay. Another thing we're looking forward to is getting a better service management. Right now, you can disable individual services, but you have to do so through environment variables. So we want to set up an UI for that allows you to stop, enable, disable, restart individual services. We also want to separate them into different containers. Oh, it's back. Yep. But we still want to use the same image, just different containers. And we also want to add previews in the dashboard on the first page for these services and extensions. So yeah, you can try it yourself. It's compatible with a lot of hardware, including x86 computers with Docker Compose. You can just try it with this command line. You can also find it on our GitHub, so bluerobotics/BlueS. We're slowly growing in popularity. It has been used extensively on ROVs and boats. It had some use on drones, not a lot so far. And we would love some more people to use it and give us feedback, and we are willing to assist you if you want to integrate a new hardware or vehicle. You can download it here. Yeah, so I just want to thank you, the Ardupilot community, for everything, and go ahead.
Planes, fixed wing, VTOL. Where is that on the plan?
It's hanging on my wall right now.
Okay.
I have a VTOL hanging on my wall.
Okay, not much good, but okay, let me know how I can help.
Oh yeah, cool. Definitely. I think right now I just need a better battery.
I think it'll basically work.
Yeah.
Any Ardupilot vehicle will basically work, but there's little details that won't work. Like the mission command list will be way too short. Like Copter doesn't have a takeoff command yet in cockpit. So there's like some basic stuff that we need to fix, but it's also easy to fix.
Okay, just want to thank Ardupilot for the great team and project, Blue Robotics for actually embracing open source, and Elliot and Patrick for helping with the slides. And now, let's try that live demo. It's going to be quick. Let's start with cockpit. Do we have? Oh, there we go. So, can you show me? Yeah, so that's all running BVLOS. That's probably me waving at the stage. All of these black spots are hit transmit requests on WebRTC, so you can see that the network is not quite happy.
But it's not bad. It's not bad.
Yeah, see, now it lost my link connection. How? Oh, there we go, okay.
Oh, it's gone.
Oh, no, I just switched pages, that's fine. We have 5 minutes, so. So yeah, just go take a brief walk through the UI here, if the Wi-Fi allows me. We have some autopilot management. You can, yeah, it's not allowing me. But yeah, this is what it looks like. I think that's plenty. You can try it yourself. I think he's gonna show me. I have to finish now.
Yeah.
So yep, that's it.
Final questions?
Any final questions? No?
All right.
Fantastic talk, both. Thank you very much. That was excellent. Next up, we've got Lee Schofield. So we'll be starting again in 5 minutes.
We will shortly be resuming APDC 2025.
If everybody could please take your seats. Please take your seats. We're about to start the next talk.
That's right, mate. No worries.
Final warning, please take your seats. Please take your seats. So our next talk is Lee Schofield, or many of you will know him as Painless 360, talking about instructing users on how to use Ardupilot.
Thank you. Good morning. For those of you that have never seen me in the flesh before, I do actually come in 3D as well as 2D. The next 20 minutes, and I am conscious I'm between you and coffee, right? So we're going to try and stay to time because I know everyone needs to be caffeinated for these things. I'm going to talk about supporting the community. Before I get into a couple of slides, what would help me would, and this is audience participation. Sorry, I'm going to do a bit of that. Of those people in the audience, please put your hand up if you talk to end users and provide them help, support, and answer their questions. Thank God for that. I'm not talking to a room of people who have no idea what I'm banging on about. Thank you for that. So what I'm going to do in the next 20 minutes is talk about the things that I do when I'm talking to the community, so that even after 20 years of doing it, yeah, I am that old, I'm still getting a kick out of talking to people, and I still look forward to engaging with the community on a daily basis. The support I'm talking about is a little bit different from the support you would provide to a prospect or a customer. This is what sometimes is referred to as the great unwashed. These are all the people out there around the world coming into the project. Now, there's loads of different ways that we can cut up the market and the people that we talk to and support. Okay, there's the classic pyramid where you guys are at the top. Everyone in this room I would consider an expert who knows what they're talking about. You're the orange bit. And then as you go down, you find that the knowledge and expertise decreases, but the number of people in that community increases exponentially. The cool thing is that there's a load of other ones, and I'm not going to go through it, because things like the competence cycle, if you want to know more about this, talk to me at lunch. But what's happening is Ardupilot as a project is becoming more and more popular, So rather than it being something that only weird people did in their bedrooms 15 years ago, they were soldering stuff together to make a UAV just to see if they could, these days it's billion-dollar business. And that's... Well, let me put it this way. Is there anybody here, when they were a kid, who didn't take their toys apart to see how they worked? Right, okay, prosecution rests. Yeah. Well, the thing is, and this is the point, that is normal for this community. We all are frustrated engineers, we have those kind of brains, and it means that when we are presented with a problem, we naturally try and break down that problem into thinking about what the actual causes could be, and we start to investigate those causes. That kind of skill is fantastically useful when you're trying to fix why your ESC doesn't work in your thing that you've just made. Lots of people coming into the community these days don't necessarily have that same wiring. They aren't the kids that took their toys apart when they were a kid, right? But then when we're trying to support them, we're trying to help them understand how to build what is a relatively complex flying robot using Ardupilot when they don't have that kind of natural instinct. So yeah, we are all a bit weird, but weird in a good way. So I'm going to go through the 6 things that I do when I'm providing free support. So for those of you that already do this, you might kind of know a little bit about this, and as I'm talking about it, you'll kind of go, yeah, I do that, right? But also, over coffee, I'd love to hear from those of you who do this to kind of give me any tips and tricks that I've missed, because everybody has our own way of doing it and what the time we put into the community and what we get out. For those of you that didn't put your hand up, the reason that this is important is the people that we are training on Ardupilot are going to be your employees and competition in 2 years' time. So this is where those new people are coming from all of us spending hours and hours in forums, YouTube, GitHub, Discord, bashing our head against brick walls, helping these individuals be able to build this stuff and fly it successfully. So here's my 6 top tips. Are you ready? Number 1, when you are going to deal with a community for free and give your time for free, emphasis on the for free, right? You're just doing it because you're giving back to the community. Have a real think before you start down this road about what you will accept, what you want to do, how often you're going to do it, when you're going to do it, what methods of communication. Are you only going to do it on Discord? Are you going to be an idiot like me, making videos on YouTube every day to answer questions? How that's all going to work. But the other side is also have a think about what you expect from the people who ask you for questions, right? You need to be clear on that, and ideally publish it in a way that you can refer to if anyone ever asks you a question that's a little bit spicy, okay? Now, usually that's part of a forum. There's a comment section, you know, that thing with the forum rules that nobody ever reads, right? But I have a couple of paragraphs under every single one of my videos that I do on YouTube that explains what my expectation is of people interacting with me, okay? It's a very, very long way of saying don't be an idiot, but basically it lays it out. And if people are not complying with that, then my responses are prorated. Does that make sense? It's good to have that because also when you start engaging with the community, those of you that already look after them, you will know that there's never only one question, right? You answer one question, it's like peeling an onion. There's at least one more, probably 2, probably a dozen. Right? And if they find somebody who's willing to help them, they will hold on to dear life, particularly if they're new into the Ardupilot community. They will hold on to you and just go, please, please, help me, help me, help me. And that's great, but some of us have families and need to sleep occasionally, so have a think about that. The next one, which kind of leads on to that, is set expectations. All right? The reason that this one is there, and the reason that this is one of my rules, is that I only provide free support via YouTube comments. But if you look, you can find my email address and you can probably get my phone number. And I get lots of emails and phone calls from people. Hi, my name's John. I've just built a quadcopter and it nearly killed me. Can you help me fix it? Right? The danger is that if you're sat on email, and email is not one of the ways I provide support, but the danger is if I'm sat there already doing email and a question comes in from somebody, and you think, I know the answer to that, I'll just send the link, and you send it off, and you reply within 5 minutes. There's somebody nodding vigorously over there. You reply in 5 minutes. That person thinks, brilliant, I've got my own tame YouTuber that can respond in 5 minutes. Let me send him the other 7 questions. If I then don't respond within 5 minutes, I get to him maybe the following day because I did something that involves, you know, normal stuff, then I'll come back and I'll probably find a spicy follow-up with like, oh, have I offended you? And I'm like, hang on a minute, I'm doing this for free. So be careful about managing your expectations. If people are contacting you outside of the routes that you have put in place to provide free support, my rule is I try and leave it 48 hours to reply to any. I'd still reply, but I don't reply quickly. And what that does, it's like training a puppy. It just gives that user the experience of, no, he will get back to you, but it's not going to be instant, and I've not set an expectation that then I'm going to regret in the future. I'm loving all the nodding, all the people who do this like, yeah, been there. Next one. I was told when I was a kid, there is no such thing as a silly question, okay? And I still absolutely believe that. I think if someone is asking a question, it's because they need help. And if I am able to help, I want to. So there's no such thing as a silly question, but there are definitely lazy and rude ones. And we get those all the time, right? The verbosity and clarity of the question that I get will directly be proportional to the length and clarity of the reply that I give. If somebody says to me, hi Lee, big fan, watch your videos all the time, building XYZ, had this problem, I've tried this, I'm really stuck, any help you can provide would be amazing, cheers John, I'm going to spend a bit of time, I'm going to write a couple of paragraphs, give them a couple of links, things to try. If it's a one-liner, I'm not going to actually show of hands who's had these, but I guess it's going to be everybody, which is something like, follow video, doesn't work, what problem, 7 exclamation marks. I can't really help with that. So what I will normally do in those instances, I still want to reply and I want to try and help, because they're obviously stuck, but my reply, and you'll see it, if you ever look at my videos, right, you'll scroll through this after this talk and you'll go, oh, he's done that. I say, what troubleshooting have you already done? Question mark. That's my standard response. Almost always, I never get a reply. The reason I never get a reply is because that individual's probably sent that exact same question to a dozen people, and he's got the response from somebody else. But if they cannot engage with me to provide some very basic information, I'm on a hiding to nothing. I'm never going to be able to help them. That leads me to the third category. Never, ever feed the trolls. Now, this is different if you're in a business. We were talking about this just before. If you're in a business and they are your customers and they're being hard work, that's tough. They give you money, you're stuck with them, right? When you're providing free support, you are allowed to dictate how you deal with these people. In the early days, I would try and, if somebody was being a little bit, let's call it spicy, right? And giving me nasty comments, either personally attacking me, someone else in the comment, oh, can't believe you're such an idiot. Whatever it is, I kind of would respond to them, usually the day after, to let any emotion drain away and say, are you okay? Right? Very, very rarely in those instances in the early days, they would reply and say something along the lines of, yeah, really sorry. I was really frustrated. I've spent all this money. I've been trying to make this Ardupilot thing fly and it just won't. I kind of took it out on you. Can you help me? Right? That happened twice. Right? The rest of it, it was all like, brilliant, I've got an audience, and it was more vitriol. I have a zero tolerance policy for people who cannot be polite and follow the rules of society. They're asking me for help for free, and it's a nice community. So my advice would be, and this was actually a piece that came from Bart, a guy called Bart at Hobby King. In the early days, I was lamenting about how nasty some people could be. And when you put yourself out there on the internet, you're going to bump into these guys and girls. He said, it's dead easy. You just don't engage with them and you delete and ban them. And I do. And that means the comment section is a much nicer place. And if someone asks a genuine question that may have been answered a million times before because they only came to Ardupilot last week, somebody isn't going to go, oh, you idiot, I can't believe you've asked that. It's so obvious. Next one. These last two are ones that I've only added, even though I've been doing this for like 20 years at this point, I've only added these in the last 18 months. So I used to only have 4 rules, so it would have been a much shorter talk if I'd have done this before. It's about symptoms, not causes. Lots and lots of the people, and there's a presentation this afternoon from a group who provide help and support to students, and they'll kind of reiterate some of this. There is this thing where people come to us and they ask for help and they report a symptom. They don't know they're reporting a symptom, but they are. My ESC won't turn my motor. What's the problem? Well, let's get the whiteboard out. There's about 12 things that we probably need to check. Helping people understand how to troubleshoot has, in the past 2 or 3 years, become more of what I do, where historically, the people in the Ardupilot community were almost all the people who took their things apart when they were a kid. It's less of that is happening. The other thing is that if I want to make a video now about helping people fix that problem, calling it Ardupilot ESC calibration demo is a really crappy title. Why is it a crappy title? Well, it's a crappy title because that's not what the person who's looking for the solution is going to search for. They're going to search for motor doesn't start until quarter throttle. That's actually what they're going to search for. So I now try and call my videos to help people what the people are going to be searching for, not what it is. Just died. No, it's back. Last one, and this has happened about 18 months ago. I was having a couple of engagements with a couple of people and really struggling. It was one of those where I was hitting my head against a brick wall. I was having the same conversation over and over again, inside, outside, for about 6 weeks, and I just couldn't understand why we weren't making any progress. And it only came about, the reason only came apparent after I was kind of going, hang on a minute, something's not right here. One of them was a 70-year-old guy with early onset dementia, and the other guy had been in a motorcycle accident and had a critical head injury, right? Some people will tell you if they have a cognitive issue when you are trying to help them. Lots of people don't. So my rule of thumb, and this is a bit of a weird one to talk about, but if you are ever in a support situation and the individual you're talking to is really struggling, or you're just like, this just doesn't make sense, just take a step back. You may be dealing with somebody with severe ADHD or some dementia, Alzheimer's, critical brain injury, all kinds of different things. So just keep that in mind. The last tip, which is part of this, is never ever get involved with a support call when you are in a grumpy mood. Right? It works the other way. So if you drove out of your drive in the morning and backed over the cat, that's not the day for you to try and help people because you will probably be spicier than you intend to be. Okay, so those are my 6 rules. The last thing as I'm wrapping up, because I am going to be on time, is a personal thank you to me as an Ardupilot pilot, someone out here in the community, for all the stuff that you do in the project and give to us, me, and all the other hundreds of thousands of people around the world for free. Massive thank you for all that you do, because I love this stuff, and I love talking about it and playing with it, and the fact that I can download it for free is quite frankly amazing. My email is at the bottom. It's lee@painless360.com. If you have a situation where you answer the same question over and over and over and over again, and we do, because new people are coming in all the time, and there isn't a modern video or piece of content that you can link them to go, that's a really great question, there's this post or this video, I am always looking for video subjects to make stuff on. Just pop me an email at lee@painless360.com. I can't guarantee I'll always get to do it, and usually poor Ben at 3DXR has to help me out doing the really complicated stuff. He's ignoring me at the moment, quite right. But do let me know, because I don't mind making content like that, because ultimately a rising tide lifts all boats. So thank you very much for your attention. I will hand over to Matt, and you can have some caffeine and crack on with the rest of your day. Thanks for your attention, and thanks for your help.
Fantastic talk. Thank you very much, Lee. Okay, we're now into the morning break, and we will be resuming out on the takeoff pads at 11 o'clock for Ferruccio Vicari's Turbine Heli demo. Thank you very much. Ladies and gentlemen, please can you head out to the takeoff and landing pad, ready to see the next demo, which will be starting in 1 minute.
We will shortly be resuming APDC 2025.
Then I will move it over the grass. Yeah. It will come.
Gentlemen, have our first demo of today. We have Ferruccio Vicari, who's going to give us a demo. We lost them. He's going to give us a demo of his Turbine helicopter. So, Ferruccio, when you're ready. So to start, Ferruccio is going to take off and do a hover check. Okay, the turbine is now starting. Ferruccio added all of the support for turbine engines into the AP Heli motors library. Bringing up to head speed now. I love the smell of Jet A1 in the morning. Okay. Ferruccio is going to put the aircraft down on the grass before initializing auto mode. Auto. Many people won't helicopter pilot for before. It shares a lot of the code with standard multicopters, so there's a very common interface. And however, it's mostly changes to the motor's back end, which allows us to fly this specific variant of copters. Okay, now Ferruccio is going to take over into acro. Doing a nod for the crowd. If any of you haven't seen it already, Ferruccio's got some fantastic videos on his YouTube channel where he flies helis for FPV. Absolutely beautiful piloting there. Thank you, Ferruccio. So just one thing I forgot to mention is that all of the head speed governing is all done within ArduPilot as well. And now we're into the turbine cool down phase, which is a part of that turbine management stuff that Ferruccio has added to the AP Motors Heli library. Just waiting for the turbine to cool. And we're done. Another round of applause, please. Okay, if everybody could return back to the venue, and we're going to start with the next presentations. Thank you.
We will shortly be resuming APDC 2025.
Okay, ladies and gentlemen, please take your seats. Please take your seats.
Next up, we have a very exciting talk from Charlie Burge and Dan Moss from Manna Drone Delivery.
Cool. Okay, we'll jump straight into it. So yes, as Matt said, we're from Manna, and we're going to go through some of the challenges and a bit of our journey over the last few years of how we do drone delivery.
Yep.
Cool. So a quick intro to ourselves. So I'm Dan. My background is in robotics. Mainly on the software side. I've been with Manna now for just over 6.5 years, and in that time, similar to Charlie, I've worn many hats, from flying to building, whereas now I'm kind of sitting on the safety systems and integration.
And then, yeah, my name's Charlie. I'm currently Manna's aircraft team lead. My background is in physics, so a bit of a different story. I also joined Manna doing software, and have worn also many hats along the way. Been at Manna for about 6 years. But it's been an exciting journey along the way.
Cool, so what we're gonna go through, we're gonna go through some of like how Manna works in general in case anyone hasn't heard about us. Go through some of the challenges and have some extra questions at the end. Do feel free to have questions throughout. If there's anything specific, just put your hand up and we'll get the mic around. So yeah, Manna, we have been operating for basically the same time that we've been in the company, so 6 years. We're a last mile delivery service, so we're solving that short problem of getting the delivery to your door. The aircraft, we carry up to 4 kilograms, and that's typically within 3 minutes. That means we can keep your hot food hot and your cold food cold. So whether it's a coffee or an ice cream, it'll arrive in good nick. Time is money, so hopefully when we get the PPP and the Ethernet, we can get quick turnaround times on the landing pads and make that even quicker. We're in 3 main locations, so not just here in Europe, we're in the US, so we're based in Texas, and then our main headquarters is in Dublin, and we also have an operation in Helsinki. Overall, Manna employs about 150 people, including operations, and we're trying to solve the broken problem of road delivery.
So I'm going to talk a little bit about how it works. So it starts with somebody putting an order in via an app. That can either be our app, so Manna has its own delivery app, or via one of the kind of like food aggregators you've got, people like Just Eat, Deliveroo, and DoorDash. That order is then prepared by one of the vendors, so that would be one of the 50 local businesses that we work out, for example, in Blanche. That order is prepared, put into an aircraft. Our system then goes and generates a flight path for it that goes and delivers, that takes us to the customer's house. And then the aircraft goes and flies that and then delivers to somebody's back garden. So we deliver from about 14 meters, and you can see here an example of an aircraft doing a delivery. It delivers the package down on a bit of string, so it winches down, and then, we leave that in somebody's garden, and they go have their takeaway or whatever it is that they're ordering. But we operate 7 days a week, and it's a service offered to thousands of people, and we do it in 97% of Irish weather.
Importantly, it's the Irish weather. Like, it's very windy, it's very rainy. I don't know why we chose this location, but it's a great test bed, so we can deliver basically anywhere and a lot of the time. This is happening right now, so we get a question a lot of the time to be like, where are you operating, how often you're operating, 7 days a week in those locations. This kind of covers how we got there. So this is, again, just a load of pictures to take in, and we're just going to go through how we kind of go through this crawl, walk, run approach. At the beginning you can see literally testing on small test beds. That's just a small 450 Discovery, and we literally went from learning quickly in the field, dirty bean bags, farmyards, whatever it was. We were a small team, iterating quickly and getting those rapid prototypes, learning all the mistakes as quickly as we could. The main problem we were trying to solve at this point was working out what drone delivery looked like. So like, there was no playbook, there was no like answer, it was just like, what do we do to solve this problem?
And then from there, we had our first prototype. You can see it there sitting there in the barn. And the next stage was like trying to take that and actually going and do operations for the first time. So we started in a place called Monagal, and we kind of scaled from there. And there we were doing only a few orders a day, but it was kind of like our proving grounds. But to get there, you need to do a lot of testing. And so you can see here some examples from the testing that we've done. You need to make sure that your testing outpaces your and environmental testing is key. So you'll see some pictures there from the snowy winters in Finland all the way to the heat in Texas. It's very key to as we say, make sure your testing is outpacing what you're kind of doing in your ops environment.
Yeah, so it was really important to close that loop between the testing, feeding it back into our operations. So we're now at the point where we've done a lot of that learning. We're still obviously learning, but we can now scale what we have. So on the third row, you can see we do a lot of automated testing. So the issue is if you bring an issue into this kind of scaling phase, it means it takes longer to close that loop. So it means you have to redesign something. You then have to go through this cold testing, hot testing, and do all that again. So the earlier you can find something, the quicker you eventually get. So we've built this confidence. We're now able to see, like you can see all the drones kind of lined up there, ready, like they just got their maintenance done there, I think. So we can build that confidence, we expand, we get that consistency. So if anyone has any kind of manufacturing line, or maintenance, or checks, or dealing with people, trying to get the same repetitive tasks over and over again is really tough. So we try and solve this with automation, and that's really key. We have robust checks for commissioning, quality control, any of the kind of pre-arm checks. Like we've taken a lot from the Ardupilot community and learning just to see what works and what we can do quickly and what takes a bit more time.
And it's worth noting that like simplicity is really key here. Like you shouldn't add anything to your process that you don't need to. but it needs to, it needs to be robust, but also keep it simple. Don't make it too complicated.
So like, you can kind of see in the middle picture on the right, like everything's kind of spaced out there, like it's a good few meters between the pads. You can be very conservative, whereas we've gained confidence, we can now fly much closer together and have the aircraft just being up and down very quickly. So safety is still like really key, obviously, and it's at the heart of everything we do. So as we grow and continue to scale, it's really important that we maintain the same safety level. So even if we're going from 100 flights to 1,000 flights to 10,000 flights, you need to maintain the same safety level through it, and keep improving it. So this is the Dublin suburb of Dublin 15, which we call Blanchardstown. This has 3 bases. You can kind of make them out as the dots between the drones.
Quite a lot. The GIF goes quite quickly, so it was what could fit in the PowerPoint at the time.
So this is 8 kilometers roughly in this whole space with the 3 bases inside there.
But just to give you an idea of what a day's worth of deliveries looks like, so you can see all the little dots flashing across the screen very quickly. There's all the little logos of the different orders that have been made. On this screen, the red dots there, they basically represent all the different deliveries that have been done previously. The size of the dot is kind of the number of orders that people have made. And then all the green dots, they're all the deliveries that were done that day. So you can see the scale of just even one of our cells, it's a lot of flights that we're doing every day, day in, day out, 7 days a week.
It's a lot of flying. I think that's probably one of the key things we're trying to show off here is like, it's a lot of flying. This is Ardupilot code flying a lot in the real world.
So next on is talking a bit about how we do reliability. So I'm going to just intro a little bit the framework that we use, just to give people a bit of context. So we fly under the European regulations, and we fly under something specifically called SORA, and that has different levels to it, and they're associated with ground risk and air risk. So in a very, 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 very simplified way, I've tried to relate these down to something, because there's a whole process that you go through to go and work this out, but I just wanted to give people who haven't been familiar with the framework a bit of a feel for what it kind of like relates to. So you can kind of approximate Sail 1 and Sail 2 to being kind of like operations over the sea, not many people at the ground, like on the ground, maybe the ship or 2 or something like that. But Sail 3, that's what we currently operate at. That is that kind of represents kind of suburbia, and then like Sail 4 plus, that's really like dense urban environments, so like city centers and things like that.
So yeah, we fly at Sail 3. We have a LUC, which is a certificate that allows us. It's just a proven certificate that lets us allow to fly in these places. We also have cross-border, so we can open up new bases using our own risk assessment, which is very useful for Europe as we scale. We have a similar thing in the US as well under the FAA. Again, that's another challenge we'll come to later, is kind of balancing Europe, America, and other places as we go around. So yeah, finding the common ground between the different solutions. We use functional-based testing. So as you can see, we have the parachute testing going on there. So that's following ASTM, 40 plus parachute things. When anyone ever asks who has crashed the most drones in Manna, this guy. Yeah, how many parachute testing is key, and repetitiveness is there.
But yeah, we've done a lot of flying hours in that time. To demonstrate it, you have to demonstrate that kind of level of reliability, you have to do a lot of flying. And right now we're sitting at over 15,000 flight hours.
Yeah. That's in all the conditions, that covers all the conditions. Because we're flying so much, that covers cold, wind, rain, wet, dark, light. We're trying to figure out
the entire flight envelope, from low wind conditions, high wind conditions, gusting, you name it, icing conditions, whatever it might be. You have to have tested in all those conditions to know the limits on your aircraft.
Another challenge we had here is defining what those are. So a lot of these are defined for manned aviation. That doesn't always equate to our kind of smaller UAS-sized aircraft. So trying to get that overlap between what was manned and what is like the drone space, we have to make up a lot of our own definitions based on the evidence that we're kind of given.
Cool. I'm going to talk a little bit now about how we actually go and demonstrate that. So this may be things people have seen before or not. It's something called CPM. It's basically a method for, people can think about it kind of like a hypothesis. People familiar with kind of hypothesis tests? People remember that kind of stuff from school? It's effectively a hypothesis test, and it's telling you about, as you fly, you can gain a confidence on like an underlying failure rate. So, for example, for this, I think this graph is for Sail 3, isn't it? So, for Sail 3, you need to have completed about 3,000 flying hours to reach 95% confidence in your aircraft's ability to fly, and that's with no failures.
That's the blue line.
So that's the blue line here. And then Dan's going to talk a little bit about what that does when you, like as you're growing and learning on the way, because it's not going to go perfect first time.
Yeah, so I wouldn't be doing my day job if we weren't trying to stay safe. So the easiest kind of way to represent this, so each kind of black dot is what you'd class as a failure, a top-level failure. As soon as you kind of get to the, I'll come over this side. So as soon as you kind of get to the higher, like 80, 90 kind of % range, if you get a failure, it will drop a lot less. So every time you get a failure, it drops straight down. So if you get to 40%, you lose a lot of confidence. And I think you get that in a personal way as well. So if you're flying something that you just built, you'd be flying it around, oh, it flips over straight away. Oh no, my confidence is kind of shattered, and I have to try and build up that confidence again. It's the same methodology for this. So yeah, you lose a lot of confidence, but you kind of have that bathtub curve. You gain your confidence back, you build up your hours. As you get it back to the top, and you keep gaining those hours, and then you learn something new, it'll drop, but not so much. And again, if you have, like, you keep those hours, you drop again, but you still maintain it. If you kept getting failures, it would drop down very quickly. So we're obviously trying to maintain a consistent number of hours to number of failures. And that kind of goes back to, as we're flying more and scaling, this becomes more prolific, because if you aggregated that all the way to like 20,000, 100,000 flights, you're going to get failures of some kind, but you need to make sure that you're still outpacing that growth.
Yeah. So kind of going back to what we mean by top-level failures, that's if anybody's done a fault tree for their aircraft, maybe people might have, people might not have done. They're the things that sit at the very, very top. And often those things don't happen from one failure. So our aircraft is single failure tolerant. So that means you can rip out any one part of the aircraft and the aircraft survives. But if you happen to have a failure where two things line up at the same time, that's one of those events for us. And it'll be different for different people. But yeah, it's a really effective way of tracking like your progress and your internal confidence. And it's a great way to demonstrate that to the regulator. So they're going to come to you and they're going to say, well, how do you know your aircraft is safe? And this is like the framework to be able to go and prove that to them.
And it's not linear, as you can see. So it's as you gain more hours and keep pushing that through, you plug it into the algorithm and you get your number. And then, yeah, we mentioned failures. So like we can definitely show some of these learnings. So we tried to put this into two buckets. We had a bit of a discussion on trying to make this in a way that was like super usable. So like people get it wrong. People are tough, and the sensors can get it wrong. And anytime that you can make a binary decision and just shorten down how many choices you have, it's a lot easier to do a root cause analysis.
So I'm sure people are kind of familiar with the common failure modes, and we've kind of gone through them all. Compasses, rangefinders, GPS on occasion, they're all great learnings that we've had in the past. I'm glad we've kind of moved away from compasses now, and they're not our primary sensor. They were a right pain.
We're using GPS baseline for yaw.
Yeah, no, we use GPS baseline for yaw. But yeah, like I mean, people are very familiar with this kind of stuff, and you've got to try and like we've solved the problem of redundancy. But when I've been talking to a lot of people around the conference actually about that, and like people say, some people maybe not convinced by redundancy. Some people think it's like some people are starting kind of venturing into that space. But yeah, you kind of need to solve the sensors problem first of all. Start with sensors, make sure that's robust, and then you can kind of then think about then taking that into architectural redundancy.
And then on the other hand, people make mistakes. There's always a thing of, if you have a square hole, if you have a round hole, someone will get a square peg and try and push it in. It's very common. We see it on the drones all the time. We'll get to it a bit later in the automation on how we solve this, but like, people, if they have a button, they will press it. So if you give them a transmitter, there's many buttons on the transmitter, so they'll try and press them all. So one thing we kind of did was start phasing out in the operations. And that was mainly from a couple of cases where we had the e-stop and mode switches accidentally being hit.
Dan, about that one, don't you, Dan?
Yeah, so we ended up having 2 e-stops pretty quickly, because when I was giving a demo to the CEO, to Bobby, we were showing off our software and we were like, this is great. Turn around, knock the switch, aircraft dropped out the sky for the testing, and then that was that demo done.
So you still need to use this kind of stuff when you're kind of like in your development phase. But for us, it became the fact that like RC became one of our biggest failure modes, and we had to phase that out. So specifically for operations, I see there's a question.
Yeah, have you got any data around that? One of the interesting things I'm facing in Canada is the regulator seems to have the attitude that we don't trust the technology. So you have to have a human in the loop to make sure that when the technology fails, the person will be there to save it. And we always seem to be telling an opposite story, but have you got data that says, oh yeah, X number of failures were due to people versus the technology and that kind of thing?
Absolutely, yeah. So, and that's kind of what drove the decision making, is that we monitor. One of the things we do is we collect a lot of data, and we make use of that data as well. And so, what happened was effectively, like, our most common failure mode was the pilot at that point. And it's probably not the case for everybody. If you're doing lots of development work in Ardupilot, you're making frequent software updates, major software updates, testing new features, you might sit at a different risk balance. Then you're testing very, very different code or whatever. But for us, we used, I kind of say to people here that we use a kind of a narrow set and kind of a well-trodden path within Ardupilot. And we've built up a lot of confidence over that time of use of that kind of like that base set.
We still do have a human in the loop. So we haven't like completely removed the human. We do need it for that sense. They just don't have a transmitter. They have 4 buttons that they can use.
So it's a much more simplified interface for the pilot. So it was just like, it was examples like that. You've got to imagine, particularly like at our test site, because we're doing such a volume of flight testing, there'll be a person sitting there, rinse and repeat, 10 flights an hour, something like that, on a single aircraft, and then maybe they're operating several aircraft at one time, and you can imagine it's quite repetitive. And it's like those kind of mistakes. Somebody the classic example that we had was, somebody lost track of their aircraft and, hit the buttons accidentally in the test site, and then, the aircraft comes under the parachute. But it's not what you want to be doing. So yeah, data drove that decision.
And it's the same thing with parameters and configuration control. Everyone always loves how many parameters we have, and then also how we control those. So for me, as well, like, we had a few different flavors of aircraft. So like for the example in this one, we had some aircraft with the flight controller facing one way, one the other way. AHRS configuration, AHRS orientation is very critical, and making sure that things linked up and you had the automation to make sure all of those checks were in place.
And that's another good point, is like, have process when you're doing your development testing as well. Have your common checklist, like you might be, like we manage configuration automatically these days, but for dev testing, you still have to, there's somebody going and changing these things. But having your tick list, make sure you've got your critical steps down, so, you've done your horizon check or something like that, make sure that, that's a very simple example, but like it's kind of making sure you've got those basis steps to make sure you're flying safe.
And like these were kind of earlier examples, so like, yeah, we keep learning, we keep adding. Like the main thing is to find out the issue, do the root cause, learn from the mistake, don't do it again. So
you've got to make sure you're always learning and improving. If you do the root cause and you don't learn from it, it's no use. And if you don't do the root cause, you really should start doing it.
And Beckett had a great quote for this. So it was like, try again, fail better. So we try and put that into everything that we do.
So a little bit about automation. I'm not going to go into too much detail, so we have a bit of time for questions as well. But there's lots of stuff that we do with automation when it comes from pre-flight checks. One of the requirements is obviously that we have no single point of failure, but that means that you also can't take off with latent failures. So we have to have lots of automated checks on board the aircraft that make sure all the systems are go before flight. There's lots of stuff that goes on inside of our flight routing system. So we actually route aircraft in 4D, and it sounds very fancy, but what that basically means is that we know where the aircraft is at any moment in time, so we can route missions around each other. And that's kind of like, if you think to the UTM space, which I'm not going to touch on, but it's kind of like, it's like heading in that direction, but we needed the solution for ourselves before we got into that. And then also things like being adaptive for weather conditions. So copters don't fly airspeed, but we have an aerodynamic body shell, and we kind of want our aircraft to be flying in the cruise phase at least. We want to be able to fly it almost more like a plane than a copter. So we had to build a whole system around that, and the key is you've got to do that in an automated way.
And then one way we've been able to, so the whole kind of scale and scope of drone delivery has kept changing over time. So how do we manage to stay developing really quickly, but also under control, but also being able to adapt as we learn? So we are able to put humans in the loop in a strategic way. So for example, like loading packages, we still don't really know exactly what a loading a package is going to look like, whether it's the vendor, whether it's us, whether it's the drone, whether it's an arm, whatever it is. We don't exactly know what that looks like. We've tried a few different ways. It's still changing. Same for ground condition monitoring, same for airspace monitoring, and any of these kind of unknown unknowns. So when there's a vendor who's delayed because, I don't know, someone forgot your source, so then they have to run over with the source and be like, oh, here's the source for your chips. How do we make sure that the aircraft still takes off on time, or we have to swap with another aircraft? So it's air traffic control management at that point.
And like the problem we're solving now is that you're having to imagine a solution that's flying thousands of flights a day. So without automation, you can't do that volume of orders. So everything that we think about day to day is in that kind of like frame of mind. It's like, how do I do this in an automated way? How do I make it safe?
Cool. So yeah, we're just trying to minimize the human interaction. And then kind of the one way we try to summarize this is within like 4 pillars. So we have automation, which really enhances safety and that vendor interaction. We then have safety. Customers wouldn't order from us if we weren't safe. And then the vendor has to provide that service to the customer.
Even just the number of vendors make a big difference to like consumer demand, for example. So
we found like vendor selection and the variety for the customer was one of the biggest drivers. So all of these kind of come together and give us viable suburb delivery. And as we've kind of gone through these hundreds of thousands of flights, we've flown to the moon, which is a very cool kind of fact. Like Ardupilot has flown to the moon, and you could say we've flown there and back and there again, because we have 3 redundanciness. So I'm sure Philip will love to claim that his cube's flown to the moon. Yeah, and then if we go on to the next slide.
Just some shout outs to people who've kind of helped us along the way, and like the people who've as well. So thank you very much to Ardupilot. It's been the launch pad for us, and it's been the launch pad, I think, for a lot of people here in this room and beyond. And thank you to KH and 3DXR as well for putting on the conference.
Yeah, we've interacted with quite a lot of you, whether it's on a technical or like a day-to-day kind of basis. We just wouldn't be able to do what we would have done without it. It's super key, and we're super open. Like, we try and stay open, and we try and give back where we can, even though we are, like we said, in that very narrow, thin...
in our little vertical.
Yeah. But yeah.
Cool.
If anyone has any other questions, that's the end of the slides.
Hi there, really interesting talk and really awesome work that you guys are doing. One of the biggest concerns that I've heard about drone delivery is noise pollution. Have you guys realized that? Have people been complaining, or?
Yeah, we definitely work on that. It's one of the things that we do. We spent a good bit of time working with manufacturers on different propellers. So it's a key part of the design process. It's definitely something that we're conscious of. We've actively worked on a solution with slightly larger props that makes about a 3 decibel reduction in noise. So we're definitely conscious of it, definitely working on it. I think it's going to be a constant evolution over years. I mean, it's a problem I think a lot of people have to deal with. The obvious thing is larger propellers because you reduce tip velocity, like people know the science in here in this room. But yeah, it's a real problem and you have to think about it. We do lots of clever stuff in routing as well. So we make sure that we try and disperse traffic over different areas of like kind of the operating area. And then we also run asymmetric routes, so you kind of like fly over one side of town to get there and another side of town to do it. It's the kind of stuff to try and be respectful. I think that's what we're trying to do. We're trying to be really respectful and engage the community on it.
Yeah. Really interesting, thank you.
Great talk, thank you. Interested in your reliability approach. How do you treat that with respect to design updates on the aircraft and also software updates? Do you reset the clock or do you kind of take that as being a continuation?
Yeah, so it really depends on the type of update. So like if we're doing something development, like really like prototype kind of testing, we have that in kind of one bucket. And then if we're doing production flights, then that will push towards our overall claim as such. So like we have the same configuration control to lock down, we have the same traceability, like it's the same process, it's just how you count it.
So we work with the regulator on a process for that. And part of the benefits of what we talked about in terms of CPM is it's continuous probability monitoring, you know? So you can be making those design updates as you're going along. The updates you have to agree that with the regulator about how you phase those in. You have a lot of freedom in your developing and testing environment, but then to get that into production, there's a process. You need to agree that with the regulator about how that process works. But then the beauty of this is it's kind of like it's measuring you as you go along. So you could start this on day one. Like there are certain cases maybe where you have like a complete revolution, you know, an architectural shift, in which case you maybe would want to set the clock back to 0 because you're not working with the same thing. But we measure ourselves in 2 ways. We measure ourselves both on like a specific generation of aircraft, but also just Manna as a whole, right? So like from day one, you know, how are we doing? What confidence do we have in ourselves? And that kind of is a bit of measure of also like your design process. How do you take that from test and then get that to operations? So it can be a bit of both,
Great, thank you.
Throw up the other test.
Oh yeah, I'll see if there's some bits and pieces going on, see if I can throw that up.
This may be more of a bar story, but I'd love sort of those failures that kicked you down the reliability chart. Like what happened and what did you learn?
Sorry, can you say that one again?
So those failures that kicked you down the reliability curve, your one failure at 3,900 hours, any interesting stories to share, or is that more of a later discussion?
That's probably more of a later discussion, but like we definitely had a few, like we were saying with the manual sticks and manual control. But like the one thing we can say is like every time that we've had one of those high level failures, the platform has performed as expected. Like EASA, like they publish their safety report, and like UAVs and UASs are still like way lower overall than like manned aviation.
I just thought I'd throw this up as well. This is currently a live view of our Blanchardstown operation. So you can see there's 3 or 4 or 5 people getting their lunch delivered to them at the moment on a Saturday. But yeah, just so people know, you can see it in real time. This is going on right now in Dublin.
Yeah, it'll switch between some of the heat map of like what we were saying with the routing, and then just the aircraft telemetry and stuff.
Switching views.
So thank you, very impressive work. My question is, do you ever need and do you have onboard collision avoidance between the drones, or all the path planning is central in your...
Yeah, we do a lot of strategic deconfliction. Like the drones each know where each of them are. And we're still, like, there's lots of work going on how we like communicate with other providers and within ourselves.
Great talk. I suspect you're familiar with Part 108 and the US proposed regulation. Can you talk a little bit about it and what's your opinion and assessment of it?
Yeah, so like I think that's another kind of conversation on the population density side of things. So whether like EASA are going to become like the provider or the facilitator. We're currently on some things on SORA 2.0, and there's a lot going towards SORA 2.5. So again, there's a bit of adjustment for that as well. So I think we'll have to wait and see for some of it.
It's quite new as well, so like it's kind of like in a review process at the moment, and probably me and Dan aren't the best people to talk to it. We sit more on the engineering side, and I'm sure there's probably someone in Manna who's better qualified to give a really detailed answer on 108. But yeah, so it's kind of like in the consultancy process. I know Manna's looking at it, but I don't know if we'll have loads and loads of detail on that.
Fantastic. Thank you very much, both. That was a fantastic talk. One more round of applause, please. Okay, next up will be Stephen Dade for his BVLOS telemetry options talk, and that will be starting in 5 minutes' time.
We will shortly be resuming APDC 2025.
Okay, please take your seats. Please take your seats. Listen in, everybody. Trying to keep on schedule. Please take your seats. Thank you very much. Okay, over to you, Stephen, for another talk on BVLOS with Ardupilot, please.
Cool, thank you. Testing, yep, that works fine. Cool. Hi, everyone. I'm Stephen Dade. I'm going to be talking about sort of BVLOS options with Ardupilot, something I've been helping people with for a number of years now. More and more people are doing BVLOS flights these days, so I thought it'd be useful to go through what your options are for a comms data link perspective, as well as little features in Ardupilot that can help you on your way with this. All right. Okay, first one. Everyone here probably knows what BVLOS is, but for the people that don't, it's beyond visual line of sight. Pilot can no longer see the vehicle clearly enough to directly control it with RC. So at that point, you are dependent upon your GCS and your data links to control the vehicle. You're likely, at that point, you're likely out of range of your typical point-to-point SIG-based, RFD-based radio systems. So you start looking at more complex data link architectures. Exact distances will vary. For things like your point-to-point radio systems, those can go out a lot longer than you can see the aircraft. RFD 900s, they can go out for 50 Ks, but that will be highly dependent upon things like the altitude of the aircraft and obstructions like terrain, hills, buildings, and so forth. So we're generally talking about, if the aircraft's more than a few kilometers away, you are most likely flying BVLOS, unless you have really, really good eyesight. So first question, looking at the requirements, well, how much there are data links out there, well, how much bandwidth do I need? How much data does Ardupilot use on its Mavlink telemetry? Under default settings, Ardupilot will typically take around 3 to 3.5 kilobytes per second. In the grand scheme of things, that's relatively small sort of bandwidth. For something like, your RFD 900s or SIG-based radios, that will use up around 50% of your available data bandwidth. If required, you can lower this. I've got a screenshot there of Mission Planner. These are what's called the stream rates in Ardupilot. Stream rates, you're basically, the GCS is telling Ardupilot how often you want Ardupilot to send the data streams back for things like the aircraft's attitude or voltage. The default for most GCSs is 4 Hertz. It will send the aircraft status down to the GCS at 4 times per second. You can make this bigger or smaller depending on your needs. If you take this down to 1 Hertz, your Mavlink data rate usually goes down to about 1 kilobyte per second. That's 1 kilobyte per second during normal steady state flight. If you're doing things like uploading, downloading parameters, waypoints and geofences, you're going to see spikes in your telemetry bandwidth. So it is something to be aware of. For things like downloading the entire parameter set from the vehicle, that's going to be quite a number of kilobytes over a very short period of time. So you do need to ensure that your data link can handle those occasional spikes in your data rate to make sure that you don't accidentally flood your radio links. You can have finer grained control of what Mavlink messages you want to send. ArduPilot will send many tens of Mavlink messages by default for everything from battery status, sensors like GPS, IMU, any other sensors you've got attached, as well as general system performance. So in some cases, you may not want all of this data. For example, you may not want to know about, the raw IMU values 4 times per second. That may be something you're less interested in. So what you can do is there's several ways to have more granular control of what Mavlink messages ArduPilot can send. You can use the set message interval Mavlink message. The GCS can tell ArduPilot, I only want you to send these particular messages. If your GCS supports that, you can use that instead of your normal stream rates. On the ArduPilot side, you can also use the stream rate parameters, which have now been renamed to the Mav rate parameters in Master 4.7 Plus, in which case ArduPilot will decide how often to send the parameters. So if you don't want the GCS to tell ArduPilot how quickly to send data, you can do that at the ArduPilot side instead. So ArduPilot will just stream the data it wants to and ignore any messages from a potentially misconfigured GCS telling it, if the GCS inadvertently starts telling ArduPilot to send everything at 10 Hertz, you can just tell ArduPilot, no, just send everything at 1 Hertz, that's good enough for me. You can also, something I discovered recently, you can load message rates onto the SD card where you can give ArduPilot a list on the SD card, a little text file saying this Mavlink message ID, then saying I want this message set every X milliseconds, I believe it's milliseconds as well. All of these methods are available on the ArduPilot wiki at that link. So there's about 3 or 4 different ways to do that, depending on what works best for you. So if 1 kilobyte a second is still too much for you, there's the Mavlink high latency protocol. This is really, really low data rate, and you are sacrificing a fair amount of knowledge about what your aircraft is doing. What the high latency protocol does is you are sending one giant Mavlink packet, the high latency 2 Mavlink message that contains essential status about your aircraft and transmits that around once per 5 seconds. So that's around a 52-byte packet every 5 seconds. So that is really, really low bandwidth. This is what you'd use for systems like LoRa, which are really, really low bandwidth, in addition to short burst data satellite communication systems. If you are using this, it's still a standard Mavlink channel. So if your GCS does decide to send stream rate requests or decides to try to download the parameters on a high latency link, ArduPilot will oblige and start flooding your high latency link with all that extra data. So you do have to be a bit careful to ensure that your GCS is not sending any requests that would result in a large amount of data being sent through that pipe. And there's a link there more about the high latency protocol in Mavlink as well. All right, my favorite bit, radio options. These are sort of the sorts of options that if you are doing BVLOS flights, practically what are the options I can use as of the time of writing, so mid-2025. There's your obvious cellular options, 4G, 5G, LTE, pick your flavor. Obviously, check your flight area is covered by your cellular system to begin with. You'd be surprised that the sorts of areas that drones tend to fly in remote areas tend to be the sorts of areas that are not covered by the telcos. The telcos are really good at covering areas where people are. If you are flying your vehicle where the people are not, you may run into coverage issues. Related to that, check the frequencies supported by, on one side, your telco, and on the other side, by the modem. Not all modems support all cellular frequencies. Not all carriers support all cellular frequencies. So make sure that you've got the right match there. Related to that, you do want to tend to use the lower frequency bands for cellular systems. Sub 1 gigahertz is really nice. So if you 900 megahertz LTE bands, generally speaking, those lower bands will have much, much greater range from the cell tower. For things like 700 megahertz band 4G, you can easily get 20 kilometers from a cell tower. However, same cell tower, if you start using your 3 gigahertz LTE bands, you're only going to get a few kilometers range because those higher LTE bands are designed for urban areas, dense coverage, lots of cell towers. And those lower frequency bands are designed for the more remote areas where you have not many people around that you still need to service, but not a lot of users. Related to that, I've had a lot of people ask, what if I want to use cellular systems when I'm out to sea, on my boat, on my aircraft? Most cases, most telcos will cover around 20 kilometers out to sea, assuming the cell tower is, close to the beach. So you can get some decent coverage out to sea if you're only remaining in that sort of coastal area. As Tridge has mentioned in his presentation, Ardupilot now has direct support via UART for a whole bunch of different cellular modems now. So you don't necessarily have to go via a companion computer like a Raspberry Pi. If you prefer, you can plug your supported modem straight into a telemetry port and go that way if you want. Satellite, my favorite. It's expensive. Satellite is really expensive. The reason for that is this, if you're using a satellite system, chances are you're using it because you have to. And the satellite providers know that and will charge accordingly. It is a lot cheaper than it used to be. 10 years ago, you were talking about dollars per megabyte sorts of fees, which did make it impractical for UAS. It is getting better, but you're still looking at satellite systems being, on average, an order of magnitude more expensive than your cellular systems. Related to that, satellite modems, and especially the antennas, are really bulky. They are not designed for UAS. It's only in the last couple of years that the satellite companies have gone and said, oh, maybe there's a market here for UAS, and have started designing smaller systems. Even so, these days, there's not many systems that will practically fit on a UAS, even the bigger ones, because when the satellite providers talk about systems that work in the air, they're usually talking about systems that will fit on your private jet, and that is a whole other size there. They're generally only a couple of systems that are small enough at the time of writing. The obvious one is your Starlink minis. If your aircraft is big enough, you could fit one of those on. Starlink minis will work fine. There's Iridium Certus as well, which is a little bit smaller, a little bit more expensive. The modems can be about, the antennas can be about yay big. They're a bit smaller than your Starlink minis. As well as there's a few other providers that do short burst data. Short burst data is kind of like, it's the SMS of the satellite world, where you are just sending a small asynchronous message that will be received later, that will be received in 60 to 90 seconds. Ardupilot does have support for some Iridium SBD systems, which you can connect via the UART directly to the system as well. And then you've also got systems like meshed radios as well, like your Silvus systems. And you could also use a second aircraft as a relay system if you wanted to as well. Nothing wrong with doing that. Dealing with multiple links, I would say if you do have multiple telemetry paths, be careful about when you are splitting your packets out and integrating them back together at the end. There are some software like Mavlink Router or MavPTP that will do this automatically, but something to be aware of is when you have Mavlink packets coming in, to make sure you deduplicate them. You don't want to have a Mavlink packet come in on one link and then maybe 2 seconds later the same packet come in on your other link, because that will really mess up your GCS. Another thing to be careful of is Ardupilot by default will bridge Mavlink messages between any Mavlink-enabled telemetry ports. If you have Mavlink message coming in on telemetry 1, it will be bridged over and spat back out on telemetry 2, if they're both Mavlink, for example. So you do have to be careful that you don't create loops where you send a command from your GCS over one link, Ardupilot bridges this, and the same command comes back to your GCS on the other link. I think I'm going. A few other considerations. Do you need real-time video? If you do, minimum of 100 kilobits a second for H.264 or 265 video. Usually you'd be looking at megabit level data rates if you're looking for high-quality video. Do you need access to any ongoing computers like SSH and so forth? Does the GCS also require multiple telemetry links? This is particularly important if your GCS is out in the middle of nowhere with your aircraft. It's no good if your aircraft has five telemetry links and your GCS has one and that one fails and you don't have connection to your vehicle anymore. If you're running GCS failsafe, make sure you figure out which GCS that refers to if you are running multiple laptops with multiple GCSs, such that if one GCS laptop fails, the aircraft does not go into GCS failsafe, even though the other GCS laptops are already still online. There's been some work done recently by Tridge and I think Peter as well, to expand out some extra parameters for having multiple GCS Mavlink IDs. Finally, quick 30 seconds on cybersecurity. Just the obvious, because you are trying to control a vehicle via comms links, make sure those comms links are protected. You don't want other people trying to control your drone. Use encryption. Don't use the default pass keys, please. I've seen too many people do that. If you're transiting the public internet for any of your links, use things like VPNs, IPsec, or Mavlink siding as well, so that you know that only the right packets are getting through and other people can't have fun with your vehicle. Additionally, if you have a choice, use UDP connections where possible. just because with TCP does not work very well in lossy comms conditions because it is constantly trying to reconnect and you just get more and more dropped packets. Brief example of what a system might look like. So this is a sort of a triple redundant system where sort of on the, is that left? Yes, on the left in the blue rectangle, you've got your aircraft. On the right, you've got your GCS. For example, you might have something like an RFD 900 as your primary link while you're still within visual line of sight of the aircraft for takeoff and landing and so forth. Then you might have a satellite and 4G connection as well, and that's negotiated via a companion computer like a Raspberry Pi via a separate telemetry port. Then on your GCS side, you've got the other end of that. You've got your the other end of your RFD 900 hooked up to one of your GCS laptops. And then below, you've got dual internet connections, possibly a cable connection and a 4G backup as well. And your satellite and 4G will transit the internet, come in via those dual connections to both of your GCS laptops. And from that sort of setup, you have a fairly redundant setup. It looks like that is very good timing. So just as they waved the sign at me. So that's a very, very quick introduction to BVLOS comms with Ardupilot. Thank you. Not sure if we've got time for questions.
Thank you very much, Stephen. Sorry, we don't have time for questions, but please do follow up with Stephen after. You can have a more in-depth chat with him then. So thank you very much, Stephen. Another round of applause, please.
Thank you.
Can I ask everyone to please stay seated? We're going to do a quick changeover for our next talk. Okay, now for our next talk on multi-UAV missions with ArduCopter and Skybrush with Gábor Vásárhelyi.
Thank you very much. Welcome, everyone. I am representing two entities now. One is Eötvös University, our research base, and the other one is Colmot Robotics, our company founded for drone swarm goals. Eötvös University is the largest university in the beautiful city of Budapest, right next to the Danube. The fun fact is that we have a statue from a contemporary artist right in the garden in front of us called the Monument to Nobel Laureates, thought as a spatial pass, that abstract thing in the bottom left corner. We always think about this as a toilet bowling the drone trajectory, so we recreated that with a real drone in the middle. Colmot Robotics is started as a spin-off company like 10 years ago. Our overall goal is to have intelligent drone swarms all around the world functioning as something that society benefits of. It was founded purely by researchers at the university 10 years ago. We do mainly software development and some hardware we have a strong research background due to the university, but we operate commercially. Most of the income is coming from software licenses from Skybrush, what I will introduce to you. We do our share with drone shows, some precision agriculture, dual use, and big R&D projects. And we operate an open core business model, which includes using Ardupilot as well, for which we are very thankful. We don't have investors, have organic growth, and all the joy and excitement of open source. The name of Colmot Robotics comes from collective motion, because at the university, these are the very complex and beautiful systems, distributed and self-organized systems that we wanted to understand and model and replicate with drone swarms. And in my opinion, the main reason why in 2021, Giorgio Parisi received the Nobel Prize for understanding such systems and not my professor Tamás Vicek, because in Rome, they had a much better experimental setup with a lot more stallings than what we have in Budapest. But we also did our share with drone swarm research, starting with a microcopter system, if any of you remember that, back in 2011. And then in 2016, we changed to Ardupilot as our base autopilot. And over the years, we increased the swarm size and have now a system in which we can operate even 100 drones autonomously in a fully self-organized manner, doing all kinds of stuff. Some videos showing how these systems look like. We basically have two different operation modes for these large-scale swarming systems. One is replicating the motion of birds, which is kind of a flocking behavior. You see these drones moving around. It's a real video. These are only communicating between each other via an ad hoc Wi-Fi network, so a ground station is not even needed, and they synchronize their motion based on the information they receive from the vicinity. And the other mode of working or cooperation and coordination is kind of a traffic situation when the drones don't have a common goal to synchronize. They have individual routes, but they have to find out how to avoid collisions in a very densely packed situation, and we demonstrated with 100 drones that this is in fact possible with our algorithms and our software and hardware stack. And in simulation, we could obviously go larger than with real drones because it's kind of cheaper. So this is the same algorithm working on 5,000 simulated drones doing self-organized, coordinated motion. Compared to that, one human operator who is doing the air traffic management can handle maybe around 7 to 10 maximum units in one area. So this is a very efficient method, and hopefully in the long term, some kind of automated method will replace the current air traffic management systems. So the drone fleet we are operating since 2016 based on Ardupilot looks, after 10 years, it already looks historical because the drone bird is changing so much. But we managed to build up a drone system which works still after 10 years. The hardware setup is something like that. We have an autopilot from the original Pixhawk family, some kind of an onboard computer. We usually don't use Raspberries, but Odroids, but they are very similar. We can have now like later better chips, typically a Wi-Fi system and a secondary radio system, and for ground truthing and for precise applications, we always use RTK-based GPS, GNSS. And on the software stack, as the low-level flight controller, we use ArduCopter plus a modeling protocol. We have our own high-level swarming algorithms running on this onboard computer, which we call flock control. It's a closed-source system, but based on the open research that we publish usually. And the ground station is running the Skybrush software I will talk about. It's open core. Basically, people are using it for drone show projects, but it can it has some kind of a mission mode in which you can operate a lot of in many applications, and we use a long list of programming languages for all this stack. The full stack of software looks like this. We also have like a full software in the loop simulation framework, which runs exactly the same software as the real drones. So it's very handy when you operate 100 drones. You have to have all different levels of simulation because it's very costly to do experiments and to do crashes. And yeah, in the early times it could happen that we were testing the algorithms right on the field without a simulation, and like you just change a switch and then 20 drones fall down that you were working on for 2 months. This is really bad, so you need a simulator. We can connect to obviously any kind of basic flight simulator, AirSim or Gazebo or whatever else. We have an open source component, AP Ardupilot Swarm Launcher. It is written by Tomáš Napus. It's on GitHub. This organizes this whole setup where not a single one, but multiple ArduCopter civil instances are executed, one for each drone, as many drones as you want. It can run basically even several hundreds easily. And on the drones, if you want to simulate this swarming behavior, you can have this flock control running on each drone, and then you get the communication between the drones as well easily. Or you can have our other software stack which handles the visual object recognition of drones, and then you have some kind of vision in the drones, and then all the drone communication is channeled into Skybrush server, the backend component of our open source ground control station that has like different extensions for different drones. So if you have heterogeneous drone types, you can even communicate through Skybrush server and look at the drones as a drone entity, and you don't have to care about all the different aspects of individual drones. And then there is a front end called Skybrush Live, in which you can operate the missions, monitor the drones, and it's highly optimized for multi-UAV usage. It's a fully open source component, the front end. This whole Skybrush ecosystem on the ground is open core. We use open source firmwares. Outdoor we use the ArduCopter. Indoors, we use the Crazyfly system. Both of them are very nice autopilot systems. We have the open core GCS components, Skybrush Server and Skybrush Live. We defined these standard, for us, these standard protocols between server and live, Flockwave and Sun formats that define these multi-drone mission and drone show types that are also available and well documented. We try to have very high quality code and transparent documentation, which is available online, and we have a Discord server on which we have already like 2,000 users in 3 years, so it's really going well, and nice discussion is going on there. And the not open part is that we have this swarm level control on the drones. We can have project level extensions for the server that are closed and it extend the capabilities of the server. And of course, we do custom solutions for custom applications. The whole Skybrush ecosystem is open source since 2022, and we really enjoyed this decision to open this, and it's a very nice feeling to be in this open source community. Okay, what we do with Skybrush, one thing that we do is that we did our own share from the drone shows. One of our earliest drone shows was actually in the UK, above Buckingham Palace Gardens, with a drone launch fireworks even. It was a Christmas show for the royal family. That was the occasion where we got the permission in the shortest time, maybe like 3.5 minutes or so. And we did many shows all around Europe, and even in China in the early days. And we have many users who use Skybrush, either the open source component, open source community version, or the enhanced professional versions for doing small and very large shows all around the world. But we use Skybrush in other modalities as well. So for example, we have a cooperation with another Hungarian company with an actual product, a crop spraying drone that is running Skybrush and doing terrain following, crop spraying very efficiently, and it's really comparable to the big companies' drones out on the market. And we have some R&D projects with Hungarian consortiums about like building up multi-drone and multi-UGV and like ground and air vehicle, like distributed surveillance for dual use. And this is kind of a short introduction how Skybrush Live looks like with a mission. You can have one extension for any kind of mission you want. You select the mission type you want to plan. You set up some input parameters, like how quickly the drone should go. You select the area and the drones and just create the mission automatically, then upload the mission to the drones. It's going very quickly. I cannot even keep up with the video. Then you switch all the drones. This is a demo for 5 drones to guided mode. That's where we operate through this companion computer. And then you can individually or as a group or as all of the drones, you can just start their motors and they will start. Individual drones status can be checked. So for example, here now 3 drones still have this pre-arm failure. So we will check what is going on, and the others start this kind of automated surveillance within this area that is there. You can communicate to individual drones, as their status, and anything that you need. You can give individual or swarm level commands to the drones. Now, all the drones are ready, so we start the rest of them. Everything is adaptive and real time. This is actually a simulator, so you have the air sim window there, seeing the drones. And anytime you can make the drones not follow the prescribed mission, but to fly them here and there, anywhere where you want. You bring them home alone or in a collective manner where they avoid each other. They can also avoid the obstacles in the area, even convex or concave. So we have written all this in this swarm level operation. And so it's a very adaptive and very flexible general framework where you can operate for the drones for any mission. And then you can like customize this whole very flexible framework for different applications. And one last thing after you land with all the drones, you usually need to check the logs for everything, and we have just released a very new tool for this. We have this Q&A style log analyzer. It's in a beta testing phase, and this is the first moment when I announced this that please go to this poplan.skybrush.io page and check it out if you have some logs to analyze. It's optimized for like questions that arise over time again and again, and then you get like a quantitative answer to this. So it's very good, useful for tuning drones and for checking whether there are any warnings and errors that appear from the log file. Okay, thank you very much for your attention. We are very thankful for the Ardupilot community, and we are here to cooperate. So if you are interested in swarming, then let's talk. Thank you very much.
Fantastic. Thank you very much, Gábor. We don't have any time to take any questions, so please do follow up with Gábor during the lunch break. A couple of little announcements from myself. There's a slight change in the schedule. We are now all going to go out to the helipad, and we're going to have the conference photo now. And as soon as we've done that, you can then have lunch. During the lunch break, because not everybody had an opportunity to fly some of the aircraft in the fun flying yesterday, our flight line crew is going to be setting up the aircraft. So during the lunch break, there is some fun flying going on as well. So please, everybody, out to the helipad. As soon as we've done that, you can have your lunch. Thank you.
Okay, ladies and gentlemen, can I please ask you to take your seats for our next talk? Please take your seats. Ladies and gentlemen, final call. Please take your seats. Thank you very much. So we're going to have our first remote talk. Please welcome Yogesh Khedar, who's going to talk about fleet management and automated operation. Over to you, Yogesh.
Thank you very much. Hello, everyone. So my name is Yogesh Khedar, and today I will be talking to you about fleet management and automated drone operation. Let me share my slides. We already had some idea about these two topics. So first, the talk by Tridge in his keynote, where we saw that multi-operator operation of an autonomous buoy is a real use case, as well as the really good talk by Manna Delivery, talking about the automated operations. I'll be talking on these topics in the context of our software platform, on which I come in a bit. We all know drone operations are very complex. They have different stages. So before flight, you have to do a lot of steps, planning, checking the weather, making sure that the geo zones are all okay. Then you have to fly. You have to take care of the logbooks, the logs. You have to do the actual flight. And then the data capture sometimes also has to be done manually. After the flight, also, you need to make sure that everything went good. You have to store the data and carry out data analysis, since that data analysis is like the most often use case of using drones. We have been working on drone operations for a long time, both on research projects as well as commercial projects, and we have realized that this is a really big problem if you want to do it more regularly. So for the past 3 years, my company, Outrick, of which I'm a co-founder and CEO, has been working on solving this problem. And we created a platform which is called Outrick OS, which allows you to control or manage your fleet from anywhere in the world, as well as carry out automated operation. So single app to carry out all the stages of drone operation, planning, flying, controlling, getting the data synchronized to the platform, as well as automated analysis. This reduces operation errors, so everything is happening in the same application. It's also much more efficient, and since the data is in the cloud, all aspects of compliance can also be taken care very easily. how it all works. So the architecture is based on cloud native technologies. So we have a backend, a server which can either sit in a publicly hosted cloud or on premise, running a Kubernetes cluster, and all the microservices related to managing different aspects of your operation as well as fleet are hosted there. Then there's a client, which we name Sky Client, which is usually run on a companion computer on the drone. And we talk to the autopilot using various SDKs. So in the case of Mavic drones, we use Mav SDK. And for DJI, there are SDKs from DJI. We have also some open source projects. So we were also not the first one, but one of the first ones to add support for Ardupilot to Mav SDK. And now there's a repository where you can try out how Mav SDK works with Ardupilot, as well as the Golang client libraries to interact with the Mav SDK server. There's another possibility to control the drone. If the operator is in the field, then he or she has mostly a ground control station, and the Sky Client can also run on that, talking to the drone over the field link. The dashboard application, which is used to control all these aspects, is a multi-platform application. So you can install it on any major operating system, as well as you can use it also in the browser. The platform is multimodal, so you are able to control different kinds of vehicles, boats, rovers, drones, docks, for example, the DJI dock here. All of these are real use cases, which we are pursuing right now with our pilot customers in the private beta phase of our application. We also support Mavlink-based autopilots as Ardupilot or PX4, as well as the DJI interfaces. Now coming to the fleet management aspect. So the first is the fleet overview, where you can see the various vehicles which are in your fleet. These can consist of Mavlink drones, as I said, or different vehicles, as well as normal security cameras or motion sensors specific for use for security applications. So one could configure, which is one of the use cases right now for us, for one of our customers, that one could configure a motion sensor to send out an alarm, and based on this alarm, flight can happen automatically. We also support STIL devices, so Ardupilot STIL or PX4 STIL, which can be used to simulate or train operators for various aspects of operations. All this information can be exported, which I mentioned before, the compliance readiness. So you can export what your fleet consists at the moment and what is the status of the fleet. Then individual devices. So for example, the autopilot can be overviewed in this view, which were the previous flights, what is the status of each flight, and different parameters can also be configured. So you can also see all the parameters, as well as you can change the parameters along with the possibility to track the changes. So you are able to know what time which parameter was changed, which is very helpful finding out what could have triggered recent, let's say, behavior of the vehicle. Also available is that all the logs which are acquired on the device, they are also synced to the cloud platform, so that you are able to see it in the dashboard. You can do also plotting for individual plots, as well as download it for further analysis. The Sky Client UI, it allows you to configure the companion computer itself. So for example, you can configure different kinds of cameras, streams. Right now, Mavlink, IP, Sony Alpha, as well as USB cameras are supported. Modems can also be configured, so APN related parameters, as well as logs coming from various services which are running on the companion computer. We use Docker Compose, so you can easily add new services to it. either directly as a Docker service or as a normal, let's say, executable or daemon services. Also able to add offline map services. So a map service can provide offline maps, either terrain data or usual satellite imagery directly from your companion computer. So that was fleet management. Now, if you want to do an automated operation, first you have to really think about geozones. These can be custom custom geozones. So, for example, you can define something is a no-fly zone, or something is your operation area, which is like the geofence in Mavlink dialect. It could be also that you also, I mean, of course, you also want to add geozone data from your specific aviation provider. And this can be done using usual web map services, or there are other possibilities which also exist. Once you have geozones settled, now you would like to create a plan. You would do that in the plan management view, where you can add, delete, or edit different kinds of mission plans, as well as you can export them in different formats. The editor allows you to carry out very complex waypoint missions, allowing also to add actions for each waypoint, which is very helpful in creating sophisticated missions. Once you have a plan, now you would like to carry out a flight. So in the mission create view, you would create a mission. Mission could be scheduled for immediate execution, or they can be scheduled for a scheduled date. They can be recurrent, so every 1 hour or every 1 day. And they can be attached with pre-flight checklist. So if the pre-flight checklist is successful, the mission will be carried out, otherwise it will not be. This allows for unattended workflows for various kinds of use cases. Again, the flight information can also be exported in PDF format, which is helpful for carrying out various operation authorization processes. The control station allows you to monitor the mission, as well as taking control in real time. It can be in the field, or it can be in a controlled environment in office. And here you can see all the various vehicles which are online. Yeah. And one possibility is for security applications. For example, you would like to carry out real-time object detection. This is also possible by simply configuring what kind of object you want to detect in the video stream. What kind of, yeah, you can also change various settings so that you can optimize the object detection pipeline. As well as one of the example from the DJI dock use case, where you can also see in real time what the dock is doing. You can control the dock. You can also see video stream from all the devices from the dock, as well as from the drone. Yeah, you can also control the gimbal camera. We support Mavlink gimbal and camera can be controlled. Also the save settings. Yeah, all the aspects of camera management is also there. You can also carry out manual flights. So simply execute a manual flight, and then all the checklists would be presented to you. You need to fulfill all the checklists, as well as provide comments, and then the manual flight can take place. All the data which is being acquired by the drone is being synced either in real time or after the flight. And this is specific for each mission. So after that, you can trigger either manual photogrammetry or automated photogrammetry can be configured. So at the end, you get 3D models or different byproducts of photogrammetry, which can also be viewed in the same dashboard. Yeah, right now we are running private beta, which will run until 21st of September, from which date we will start our public beta. And at this point, also mapping missions will be supported, as well as automated photogrammetry pipeline combined with the object tracking module for video stream. Later on, we also plan to add more features, for example, AirSim-based flight simulation and training, firmware upgrade directly from the SkyClient UI, as well as offline map services. And yeah, more important is also mission sharing, which is also really important feature. Yeah, thank you very much for listening to me. Yeah, and I would now take questions.
Fantastic. Thank you very much, Yogesh. Round of applause, please. Do we have any questions for Yogesh? Okay, thank you very much. Thank you again, Yogesh. And so next up, we've got George Zogopoulos. So if you give us a few minutes and we'll resume at 2 o'clock. Thank you very much. Okay, getting ready for our next talk. Can everyone please take your seats? Please take your seats. Final call. Please take your seats. Please take your seats. For our next talk, we have George Zogopoulos talking about an exploration of TECS parameters. Over to you, George.
Thank you, Matt. Hello, everyone. It's an excellent conference so far. I'm glad I took the 1 hour trip to get here. For those who don't know me, I am George. I am a member of the developers team of Ardupilot. And I have my own consultancy, Controlled Ascent, doing Ardupilot related development, features, etc. And today I want to continue last year's, I'm trying to make it a sort of tradition to talk about TECS and other controllers of Ardupilot. And it's not going to be as math heavy as last year. I wanted to keep improving my and everyone else's understanding of the TECS controller. It's the controller that regulates for our airplane side of Ardupilot, the altitude and airspeed. And Paul had laid all the foundation, Paul Riseborough, all the foundation and all of the features for this, but we need people to maintain constant knowledge of our controllers, and I'm trying to get to that place. And it's also for personal motives, because we often get questions about tuning the TECS controller that I don't know how to answer well. So I thought this year, let's try to improve this situation a bit. And I organized sort of not an experiment, but an exploration. And in the first part, I'll try to explain what I did. So I wanted to see what each of the main TECS parameters, how it affects the performance of an aircraft. I didn't really have time to do this in a real aircraft, so I said, okay, I know how to do a simulation, let's do that. So first thing would be to construct a repeatable TECS mission to highlight all of the important features, then build a parameter sampling system, then decide which parameters I wanted to scan, because as you all know, we have a lot of parameters, extract some metrics and analyze the results. So starting with a simple mission, I created an auto test. We run thousands of auto tests every day in our CI suite. So I said, okay, let's make an auto test. It's simple enough. It's the quickest way to run the same mission and again and again. And this is just a straight line with altitude changes. This is definition of continuous waypoints that gets you through a mission whose altitude profile looks sort of like this. You have a very small, actually have a mouse, I should have a mouse for this. Maybe I can do it with a mouse, let's see. Apparently not, okay. A small step altitude up, a small descent, and then a continuous climb at maximum climb rate, and then a continuous descent at maximum sink rate. That's the mission every run from now on that you'll see is going through. That auto test is available at the branch, so it's accessible code. Yes, Thomas?
Hello. What's the missing bit?
It's, so each color is an active waypoint. And there's a blank between the climb and the descent because I interjected another section, another waypoint to let the altitude stabilize before I started the descent. Otherwise, the climb dynamics would affect the descent onset. Yeah. And this Autodesk loads each time a custom parameter file. Which parameter file basically controls which parameter I would tweak and set into a new value every time. So how do I sample those parameters then? I wrote a few custom Python files which basically allow me to define sample cases. For example, this is one sample case where I want to sweep text time constant parameter from the value 1 to value 10 with 10 samples in between. And I want also to repeat this for these values of the pitch to servo time constant. So basically, as many lists are put into every sampling case, the external product of those values is going to be run. So this sample ends up being 10 times 6, 60 times this mission. Each mission, for recoverability purposes, gets a unique name which starts with a primary parameter and its value that is being swept, and also a hash, which basically corresponds to the exact different custom parameters that were run. So if we know which parameters we want to run and sample, we can find out if we have already run this mission and recover it for analysis purposes. Yep. So these were more or less the parameters I swept, most of the text and a few ones on the pitch control. It's more than 260 runs, close to 300 now. The total size is 1-2 gigabytes. It's not that much. All of these can be simulated within 10, 15 minutes, depending on your machine, and can be analyzed even faster, I think. And the analysis is, again, through a Python files, through normal PyModeling tools. The DF reader, the data flash reader library that we have is plenty. It's reasonably quick, but I still, because I iterated a lot and added and said, okay, let's add one more sample case and one more sample case, I also set it to scan on only the new files. I also have a last file.txt with a timestamp, after which it knows, okay, these files are new, I need to go through them. And because of the way the data flash parser works, we can only isolate and log and read only the topics, the messages that are of interest for our analysis. So the script goes through the log, and extracts some metrics. I'll let you know which in a minute, and stores those values into a database. Whenever I have a personal project, tiny one, experimental one, that needs a database, I go to TinyDB. It's a Python library that gives you a database-like API through a local file, a JSON file, which is great because it's human readable and human editable. So it's great for experimentation. And in this case, you can see that, for example, for this log name, for the climb section of the log, I had this metric with this value, this metric with a null value, et cetera, which is really easy to test and inspect if what comes out makes sense. And finally, it's a third script that does the analysis. And for every log, it plots me a grid of plots that on the x-axis has the parameter under sweep, and on the y-axis, each metric that I want to see how it behaved. And let's see what each of these metrics are. The top two rows are about oscillations. So ideally, you don't want to see data points there. If there's no data point, it means there is no oscillation. The first the first column is about airspeed oscillation, frequency and amplitude. The center column is about altitude oscillation. And the third one is about the pitch reference command that TECS generates. And the lower side is for airspeed overshoot and undershoot, separately set. I think it makes a lot of sense. In the center, altitude rise time and altitude overshoot in %. And the last one I tagged later, which is the error on the climb rate, because we often have questions about why doesn't my plane climb as fast as I have set it, and I know it can. So this is an interesting one too. A note about the oscillations and how they are recorded. It's a fast Fourier transform through that section of the log. So you can extract all of the frequency components of your log, amplitude and frequency. But of course, you don't want to see noise in there. So I did a simple thresholding both on the amplitude side. Don't show me too small oscillations. It doesn't make sense to detect an oscillation in pitch of 0.1 degree. And don't show me too slow of an oscillation. And I think I put the threshold around a fifth of a hertz or something like that. Basically, don't show me transient responses. Don't show me their frequency. I want to see sustained oscillations. Another important aspect of the methodology is whether each run, if I run it multiple times with the same parameters, are they repeatable? Do I get the same metrics? Or is it just accidental data there? And it's quite good for stable flights. The x-axis, I know it's hard to read, but the x-axis in this case is from 9.2 seconds rise time, for example, to 9.5 seconds. So this is a pretty good group. Same for airspeed, undershoot, and overshoot. We were expecting ideally straight lines here. And same for the climb rate. And since this is a stable tune, you see no oscillation on the top rows. For a not so stable tune, where we had, for example, the time constant was set to something small and the pitch response was set to very weak, we see oscillations recorded, which are also reasonably repeatable. Amplitudes in pitch from 6 to 10 degrees. The frequency is also quite well grouped. So that's a happy picture. For worse oscillations and for really unstable configurations, however, no, it's all over the place. The range in metrics is quite wide, which means that, yeah, this methodology doesn't do a very good job on assessing really unstable configurations. Maybe a point of improvement in the future, but then again, when you have a really dynamic and unstable system, you don't expect repeatable behavior anyway. So yeah, I don't know what to tell you there. Any questions so far?
Right, I probably want to ask just one small question, pretty dumb. But just wondering, when you mention in a stable flight, do you mean in any specific kind of drones or any drones in stable flight stage? Or I'm not sure how do you define that?
Yeah, so again, this is only about airplanes flying as an airplane, like straight producing lift with her wings. And when I mean stable, I mean that it is flying on a constant airspeed and at a constant flight path angle, basically, constant pitch. It might be climbing, it might be descending, it might be flying straight, as long as its pitch and flight path angle is constant.
Okay, in a constant, consistent stage, that kind of. If
Sorry?
I understand it correctly, it has to be in a constant moving stage, or.
Yeah, yeah.
Right.
It's moving, but the airspeed and the flight path angle are as close to constant as possible.
Okay.
Whereas if it has a pronounced long-term period and dropping in altitude and gaining airspeed and vice versa, this is considered unstable or badly tuned, however you call it.
Okay, thank you very much.
We have another question back.
Hi. So maybe I missed it, but are these just normal CIDL simulations, or did you use something else?
This is the default vanilla CIDL of the plane.
Okay, thank you very much.
Yeah. So, for the second part, some findings that I stumbled upon or I wanted to answer through this search. It's not exhaustive about TECS. It's not 100% conclusive about TECS. Just think it was interesting and I wanted to share it with you. So first of all, talking about the TECS time constant, which is probably the primary parameter that dictates the behavior of TECS. It's a parameter that says how fast or how slow should TECS act to regulate that airspeed and altitude. Let's see if I have notes here. I'm missing my notes. Okay. So as you can see and expect, we see that when the values are very low, 1 or 2, which are unreasonably small values to put on TECS time constant, we get oscillation and overshoot, for example, in airspeed, and very small rise time, yes, but also quite a bit of altitude overshoot. So this is a first indication that our methodology reflects our expectation a bit. But you also see that for this particular pitch tune of the vehicle, setting the TECS time constant more than the minimum value to guarantee stability doesn't really alter the behavior. Yes, it kind of makes for a more pronounced airspeed overshoot or undershoot, but not by a huge amount. Again, with a caveat that this refers to the default model in the CIDL suite. So in your actual airplane, the minimum value of TECS time constant that needs to be put to make it stable will not be the same. It's not going to be 2. It's going to be something else. We're looking at the qualitative behavior of the graphs here, not the quantitative one. The next one is TECS HDEM time constant, which is how fast the altitude demand is going to rise. So when you click on the map, on guided mode, for example, and say, go here at 200 meters altitude while you are on 100 meters, usually you get a ramp-like increase in altitude, but there are also cases for, especially for small altitude increases or decreases, where the TECS is commanded to immediately change its altitude target. And this is how fast or how slow this is going to change. Basically, how much that altitude step gets curbed. And we see that increasing this parameter, this time constant, as we expect, it brings an increase in altitude rise time, That's good to see for step ups and step downs. It also decreases altitude overshoot because you climb more carefully to your final altitude. It also decreases airspeed overshoot as you make it greater. So in some cases, if you don't need that high of the climb rate performance, it's a good parameter to increase, get a less fast climbing or fast descending airplane, but a more stable one. You can overdo it though, as you can see that past some point, the climb rate error and the sink rate error start to increase as well. And we'll talk a bit more about them in the next slides. In the next section, I want to touch upon the pitch control influence on the TECS tuning. So TECS produces a pitch reference, a pitch command, that it expects to be carried out and served by the pitch control loop. But the pitch control loop isn't ideal. It might be loosely tuned, and this is an example of this is on the top figure, where the green line is the commanded pitch angle, and the blue line is the achieved pitch angle. It doesn't reach the commanded angle, and also takes a long time to reach its minimum value in this case. It takes 2 seconds. And in order to reproduce this, I think I reduced a lot the pitch to servo time constant. It is also possible to overdo it and overtune your pitch loop and cause instabilities, and this is the case of the second picture, where your green line is roughly around 0, but your response is swinging up and down a lot, and this is basically an unstable aircraft. It is kind of a given that an unstable aircraft in the pitch angle is not going to fly well anyways, but it's good to confirm it with the analysis as well. So in the right, it's a case of a very weak pitch tune. On the left, it's the nominal case. So indeed, we see that we get looser pitch when we get a looser pitch regulation, yes, as we expect, we see worse oscillations on the airspeed regulation as well. We see worse oscillations in the climb rate. We do not climb as steadily as in the nominal case. And there is also, of course, more oscillation on the pitch reference itself, which doesn't help us anyways. There are, yes, and the metrics show the same story, more or less. This is a sweep of the pitch to servo time constant. And yes, we see that when we make this value bigger, which means we intentionally make the pitch control more loose, more weak, we start seeing after some point oscillations in the pitch command, in the airspeed command, and there's more altitude overshoot and worse behavior in general. This particular feature here, it's a quirk of the metrics where the rise time doesn't actually reduce. It's that the sweep is so wild, the uncontrollability of the pitch angle is so wide, is so big that the plane shoots up above the target altitude, completely out of control, and the metrics think, okay, I've reached my altitude, yes, but in a very uncontrollable method. So it's not really a reduction of rise time. The next parameter I want to talk about is the TECS integral gain. This is a parameter that says how much various integrators on airspeed and altitude wind up to help your pitch angle and your throttle match your reference and close down airspeed and altitude errors. And let's see. You do need, the story here is that this needs to be a non-zero value. If you set this value to 0, there is no more mechanism to close down the airspeed errors and the altitude errors. And you see here that there is 500 meters worth of altitude error, and the airspeed undershoot is 10 meters, or yeah, it's really not good control. You do need some minimum value on TECS integral gain. But you can also overdo it, and again, for the default settle plane, after the value of approximately 1, you start getting oscillations on pitch because the contribution of TECS integral gain becomes unstable. Next, about TECS pitch damp, and this one, at least to my interpretation of the code and the dynamics, although it says damp in its name, it acts more like a proportional gain on the pitch angle. There are other mechanisms to regulate the pitch angle. There's a feed-forward term, which is usually not fast enough. There are some integrators, but they are also slow, like pitch inter-gain, as we said before. So TECS pitch damp can help you increase the dynamics of your pitch and get you a more tight exchange of energy between airspeed and altitude. But again, you can overdo it. If you put TECS pitch damp too high, you get oscillations again and really bad climb rate error. Unfortunately for the default simulation model, the beneficial effect of TECS pitch damp isn't very visible. There is no value here where it improves things. It can only make things worse. So in the future, I'd like to find a better example, essentially, a combination of parameters, physical parameters of a vehicle that show how TECS pitch damp helps you more in practice, more in visible terms. And this brings us to a point where we often get questions about my TECS, my plane doesn't perform well. It climbs, it loses altitude, it varies in airspeed, throttle doesn't work right. Is it a throttle issue? Is it a pitch issue? Well, usually it's a bit of both because both systems have some spillover between them. In theory, the guidelines say that if there's something with your pitch regulation, then you will see a lot of energy exchange between your airspeed and your altitude. Essentially, you will get a lot of airspeed, lose altitude, and then trade back this energy, gain altitude, lose airspeed, and vice versa. Whereas if there's something wrong with your throttle, you will see that both of these states, energy and altitude, will increase and decrease at the same time. But this is not enough of a lead most of the time in my experience. For example, if you issue an altitude rise demand, as in a constant climb change, both the throttle and the pitch need to rise by definition. And if you get oscillations and bad behavior there, it's not clear what is at fault there. So there is some logging that can help us try to identify issues. And there are logged messages that help us reconstruct the throttle signal and the pitch signal. And we can see which one of those components, we can try to find a component that is swinging the wildest or is producing the most oscillation. So in this case, from this particular log, we can see that we see oscillation, and the throttle doesn't oscillate as much, but we get a lot of variations suddenly on the pitch demand sources. And perhaps we can try to trace this one level to the back as well and try to see what does our energy and our energy balance do. And in this case, we can see that the energy balance rate request was not served right. It was swinging and overshooting wildly on this step response. So in this case, we see that something is wrong with our energy balance rate. So probably there's something wrong with our pitch regulation. And indeed, this was the case where I had set the pitch tuning to be very weak. So this is a framework to think about TECS issues. But again, there's a lot of coupling, unfortunately, and there are no hard and fast answers, at least to my experience so far. Another note about max climb and max sync performance. You get oftentimes when you have gone through the TECS calibration guides, who say that please fly in FPWA at max throttle at your cruise airspeed and record your pitch angle, maximum, minimum, etc., etc. But you still get this behavior where your pitch angle reaches its maximum and then dips and then climbs again, dips and climbs again, or under your maximum pitch. This is a signal that and this can happen as well even below your maximum pitch angle. And the reason this happens is that TECS will ease off the stick in a sense, will stop climbing as fast or sinking as fast when either of two conditions are true. Either it's expecting to exceed its maximum pitch angle, or it is actually exceeding and reaching the maximum throttle. In most situations, you have the case where the throttle is not at maximum yet, but your pitch angle is close to maximum. And in these cases, it means that it's the pitch angle that is triggering this ease off. And in this case, you can increase the pitch lim max of your vehicle, or if your TECS limit is a bit lower, TECS pitch max, I think is the parameter name, you can raise them a bit without penalty. It's not critical that they are exactly at where you want them to be for this climb. They can be a bit higher. But the TECS will never do a climb at maximum throttle. Even though the original algorithm back from the 80s was designed to do this, our current implementation will not allow it. The best you can do is to try to climb with 90-ish% throttle for a normal cruise. For cases like takeoff and stall, yes, it will try to put maximum energy, but in a normal climb, normal flight, it will never climb at 100% throttle. And after this investigation, I'm kind of getting ideas on whether it's safe to bring this back and under what conditions we can try to achieve this. Because for some people, achieving the maximum possible climb rate is important. TECS throttle damp is another parameter that is often considered for tuning. In this simulation model, again, it didn't have much of an effect, of a beneficial effect, at least. Even at zero, the plane flies fine. But at least we can see, even in the simulation, the damping effect of TECS throttle damp. As we increase its value up to 5 or more, we get increased altitude rise times, increased altitude overshoots. It smooths things out, but also makes them slower, so you get less of a crisp response in terms of altitude. And finally, some miscellaneous points. TECS height omega. This by default does not have any effect because if the EKF runs, is active, and can give a vertical speed reading, then TECS height omega doesn't apply, is not taken into consideration. So for most users, most modern users, it doesn't matter. However, TECS speed omega is used and should not be set to 0. If you set it to 0, you basically have no pin, no point of reference for your airspeed. Your airspeed sensor is not going to be used, and only your accelerometer, for better or worse, is going to inform the development of the airspeed. So don't set it to 0. By default, it's going to fly fine. Yeah, thank you. So future work, at least for me, is try to improve the scripts a bit more to give the opportunity to run every simulation multiple times, and instead of plotting a single line, plot a confidence interval of this graph, which will inform whether each graph is telling a consistent story or it's just random noise. And as I said before, try to have a system, a way where you can try this in more vehicles, more simulation models, tweak their parameters, try to bring out more bad behaviors, and try to find cases where some parameters indeed prove a lot more beneficial than in the default case. To leave you off, all of those graphs you saw before, such as this one and this one, are made with Plot Juggler. It's a plotting tool, and my layout can be found in the first link up there. You can load the log, load my layout, and get those graphs. And I also maintain a Draw.io set of diagrams where I try to make abstracts of Ardupilot controllers and other relations. And I have also tried to make an abstract of the TECS controller, and you can find this in the second link. So, thanks for your attention. I am interested to hear your experiences about TECS, and some of you have already approached me. If you want, come find me after that. And if you have TECS-related issues, send me the log, let me know. I'm all for gathering more data and helping me inform my future advice. So yeah, thank you. If we have time for questions, Matt?
Okay, we've got time for one question.
Yeah. Yeah, sure. Yeah.
Of course, you know that I'm very interested in the climb rate.
Yeah, I know.
And trying to read between the lines, there's a lot of data here, but so I think you started out by saying that TECS time constant is the most influential TECS parameter, but you also mentioned that TECS HDEM const is important for the climb rate. So it seemed a little bit to me like looking at increasing both of those parameters might help with improving the climb rate, you know, on vehicles where climb is important.
Yes, it depends. It depends on whether your oscillation, for example, is due to abrupt change of altitude, or if this oscillation persists even through steady state.
No, I mean, I'm not concerned about oscillation. I'm concerned about achieving the maximum achievable climb rate.
In this case, the more relevant discussion is the slide where I was talking about the max climb rate and in which conditions the TECS will ease off the stick and try to climb more slowly, where you have the maximum climb rate condition. And as I said, TECS will never try to climb at 100% throttle. So if this is something you expect it to do, it will never do this for you right now. Yeah.
Thank you.
Okay, we have time for a question from Troj as well.
Okay.
Thanks for the great talk, George. One thing that long-term aim we've had with TECS for quite a while has been to get a TECS auto-tuner going. With your exploration of the parameters and sensitivity, have you had any ideas along the lines of an approach for automatic TECS tuning?
It has crossed my mind. So I was talking yesterday with Nathan about one of the last GSOC projects we had, where there was reinforcement learning around tuning the TECS parameters. That could be one approach. Another more easy approach, perhaps, because users are still struggling with it, is to automate the TECS limits maneuvers to the TECS maneuvers that we have to do to find the aircraft limits, for climb rate, maximum pitch angle, et cetera, But these, for us, we know what we have to do to get these, but other users, it's not as easy for them. But tuning the stability parameters, it's a different question. I think I could get to a state where we could inform we could have an informed order of tuning parameters, like we do for our PAD games, for example, where we usually start with a P, then with the I, then with a D. I would like to get to a point where we know the order of parameters to tune for TECS. But so far, no, I don't have something like that. One idea is if we can do an adequately good job of linearization of the TECS controller, at least for the trim case, then we could do the equivalent of system identification, like we do for Copter, and then use the linear model of TECS to get a crisp and oscillation-free response with the equivalent tuning of parameters without even a simulation, just on paper. Yeah. Thank you for the question.
Thank you very much. One more round of applause, please. Can I kindly ask you all to stay seated? We'll do a quick changeover now for Bob Entwistle and Cameron Boyd.
Can you hear us? Excellent.
Okay. So now for our next talk, which is the Design, Build, Fly, how ArduPilot enhances aerospace engineering education with Bob Entwistle and Cameron Boyd. Over to you guys.
Thanks, Matt. This is our talk. We know that we sit in front of you guys and coffee, much like Lee's was earlier. So our talk's going to be quite photo and image-based. So hopefully it's just a nice thing on your eyes that you can hear and see what we get up to. Our talk's going to be mostly around the design, build, fly project-based teaching that we do for aerospace engineering students. The presentation is going to cover some introductions on who we are, what we do, and why we're here. Cover some educational use cases of ArduPilot through our fixed wing project, our group design projects, and then also look at some of the autopilot resources we use. And then we'll hopefully just discuss some of the challenges we see using ArduPilot in education for aerospace students, and hopefully get some feedback from you guys through later discussions as the conference goes on. So start off with, who are we? We are Sotin UAV, which is a research unit that does teaching, does commercial enterprise activities within the university, and also does research. And this talk is focused very much on our teaching outputs that we do at the University of Southampton.
Hi everyone, I'm Cameron. It's great to be here. So I'll quickly go over not so much the student-facing side of it, but a little bit about the aircraft that we have worked on as part of our work. So on the very left, we've got an example of, well, our 35-kilogram, 4-meter wingspan fixed-wing aircraft known as Spotter. This has been kind of the workhorse for the last 10 years. You can see a great photo there in the bottom left. That's at Farnborough Air Show. It's just flying over the red arrows. You can see just under the right wing. We've also performed BVLOS operations. The middle section shows photos of an aircraft that we named Valerie, and this was used for active volcano monitoring. So this is some video and photos from a flight that took place in Guatemala up to the summit of Volcan de Fuego, where it would perform both visual inspections of the state of the volcano. It was constantly going off when we were there, but you know, every like 30 minutes, this volcano would explode. And it was also looking at collecting ash samples to bring them back down for future analyzing. As well as fixed-wing aircraft and VTOL aircraft, we also work on multi-rotor aircraft as well. You can see an example in the top right. This is P-drone, or persistent drone. The idea of this drone is it's powered by, or it recharges with large solar panels, and then it can use microsensors, or it can move microsensors around an environment. The idea being that they're very cheap to make, and you can make loads of them and disperse sensors into the environment and reposition them. And then in the bottom right, project that was fire drone. So this was having a multi-rotor that's capable of taking a payload around 5 kilograms, developed by another university in France. And the design of this aircraft was to have everything enclosed, to keep it away from smoke and heat, and as well to be used by firefighters with, say, you know, quite thick gloves on. So everything on that is big latches, big, you know, removable arms. So that's a little bit about the aircraft that we have in our premises. So why are we here? We want to share our experiences with you. So we're a little bit different in that we're educators, so we don't have, you know, a product to sell. We're not developers, so we do enjoy, you know, getting involved with the code base. And hopefully we can show you what we do and how that's going to shape our future teaching efforts, and hopefully have a chance to collaborate with you all. And there's already been things that we've picked up on that's really interesting that we're going to feed back into our education programs. So the students will come across us in their studies. The first is in their second year, where they're tasked with building a fixed-wing wing. So we provide them with a fuselage, and they go away in teams and design a wing for it. And then the second is later on in their studies, in their fourth year, where they'll do a group design project, or a GDP, where the projects are a bit bigger, you know, a bit more money towards it. And that is where they really get involved with the ArduPilot resources and the ArduPilot software.
So to start talking about the student design, build, fly projects, We're going to start off with the fixed wing project. This is where the students in their second year are tasked to build a wing and a Arduino-controlled gimbal system. And their challenge is to make that wing have the largest speed range. And that's the difference between the maximum speed and the minimum speed. And they are asked to design some high-lift devices on there. For the gimbal, they are making it as small and as lightweight as possible using an Arduino, and it's got to try and correct pitch and roll and keep it level. And we put a little camera system on there to get live video feedback. Finally, we limit them on materials, so we stick them to working with plywoods and the solar film covering, partially because it makes it cheaper for us to operate, but also exotic materials like carbon fiber probably will make this project a little bit too easy for them to apply their structural engineering skills at this point. And they get about 12 weeks to start from absolutely nothing to getting to the flying field and seeing their design prototype fly and see how well it performs. We test the system in a couple of stages, some of which in the lab, which we'll talk about in a second. But when we get to the flying field, we have about 3 phases of a, I'm going to say, semi-automated flight test. And if we ignore the takeoff and landing sections, we put them into a low-speed race course. And this is where we set the cruise speed as unfeasibly low as possible, and we essentially test Ardupilot's stall prevention feature. We deploy the high-lift devices, and we attempt to do 3 orbits of that. Depending on how windy the day is and how well they've actually made their wing to fly as slow as possible, we would maybe get less than 3. After that, we switch to a high-speed circuit, and this is where it becomes slightly semi-automated, and that's because we use the throttle nudge feature to bring the throttle up to 100%, and we've cleared up the high-lift devices. And again, we try to do 3 high-speed circuits. Again, we might not manage 3 because their design might be really draggy, or the high-lift devices might not have fully retracted, and therefore we've got this heavily draggy system. Following that, we do some manual handling, and this can be quite an exciting moment of the flight test, because it turns out fly-by-wire A and Auto are very good at masking trim conditions and asymmetric lifting on the wings. And so if you do have an asymmetric flap deployment or retract, when you switch to manual, the pilot has to work a little bit hard to correct that. And that's to see, we do the manual handling to see how responsive the aircraft is from a pilot's perspective. So that covers the kind of automated mission side of things. But when the students are there, we used to just put the aircraft in the sky and call out what we thought the minimum and maximum speeds were from the routes. But we've decided to kind of apply our knowledge of the Ardupilot system, and we've created a live data dashboard that is suited for the task at hand. And so on there, we have some little widgets that show the data that the students need to see. So I can try and use a mouse on here. So down here, we have the minimum speed and the maximum speed and the throttle percentage. And they are doing some live 3-second averaging based on some flight conditions. And we'll cover this a little bit later when we talk about the autopilot resources. So they get a live idea of how well their wing has performed. But then after that, we do some log analysis to get a true-ish reading of their minimum speed and maximum speed. And then they can compare that against their predictions. During the flight, they also have their gimbal giving a live camera feed down. The good ones, you actually can understand what's happening. The bad ones, where they've tried to implement their understanding of PID control, you might get a little bit motion sick when you're actually watching the data dashboard. But to test the gimbal, we actually do some testing inside in the lab, and Cameron's going to talk briefly about that.
Yeah, so here we have one of the gimbals on the, so we have a custom tilt table that we've made. It's basically just a swash plate that's upside down. And we can use this to put in roll and pitch perturbations. We can also apply vibration to it as well by shaking the stepper motors very quickly. So above the green section, that is where the student gimbal will be placed. You can see the red 3D printed parts. That's a mock-up that we give them. Basically, that gets swapped out by an air unit when we do the actual flight test. You'll see the vertical cylinder on the 3D printed part. That's because when we do the testing to get a quantitative value for the student's grade, we put a laser pointer into that gimbal. That points up onto a sheet of paper, and then we take a long exposure photo, 60 seconds, from top down, and then we run a simulated flight with the tilt table. Obviously, the students are watching at this point, so they get a really good visual representation of how well their system's working, how well it's going to stabilize the camera once we have it on the aircraft. And then we use computer vision to grade the individual images. And you can see on the top left a really good gimbal, so obviously that laser pointer dot's concentrated to the center, and then below it a not so good gimbal where it's gone outside of the bounding boxes and got a lower score. We also test the wing before it flies, so we do a kind of an airworthiness test. We test it in bending, so we prescribe hanging points on the wing, which are given to the students as a kind of interface document. So they have to build those into it. And then when we test their wing, we invert it, we hang it onto a frame in the center, and then at a certain span-wise distance, we hang a mass from it. And then with an inclinometer that's placed into the little box there, you can see in the top left, we can get an idea of how much the wing is bending. We then also find the flexural axis, and then we hang a mass forward of it, and we see how much it twists. So then the students have an idea of how much the wing bends and how much it twists. And then the students get graded, and we have these radar plots where you can see the different attributes of their design for their final score.
The undergraduates, we see about 250 aerospace engineers coming through. And for us to be able to do that project, we actually only take on about 70 students. So there are other projects that the students see that we aren't involved in as much, but it might be interesting for you guys to get an idea of where else ArduPilot is being used across the university in the teaching. And so one of those projects is a CubeSat project, where the students are asked to create a CubeSat-sized prototype, and they place that on a low friction environment platform. So that's the section at the bottom, that kind of round disc. And they use some ducted fans to make that essentially sit on an air cushion. And their challenge for this side of the project is to use reaction wheels similar to you would in space to align their CubeSat to a light source representing the sun, and that's shown in the center image. And then they also have to get it to translate on a very low friction surface to try and mimic using thrusters in space. And that system is using an Ardu rover flight controller inside. Along similar lines to the fixed wing project, there is also a multi-rotor one in which the design brief is very similar. They have to also implement an Arduino-controlled camera, and that is to level it in pitch and roll, and then also to lock it to airframe body kind of axes. And the way this works is also to try and separate the design and structure side of things from the systems and control side of things. So we try and teach them the control architecture through small Arduino projects, which we can then place on larger projects, such as building the structure and the airframe around it. The next time we normally see students, from our perspective, is when they get into their fourth year of a master's or an integrated master's course, and it's during their group design projects, or GDPs. We see the teams that build and design UAVs, but there are a whole host of other projects that go on at the university. Their task for the UAV project is to design and build a UAV following a design brief of some description, and it's a vast array of different design briefs. And they get the full 2 semesters of their course, design it, so about 8 months, and we see a whole multitude of different platforms, designs, and things come through. The whole point of the group design projects is for them to put that theory that they've learned and where they've worked out how to design the perfect thing on paper and in a computer, and actually make it into a reality and see the real-world challenges that go with that. So it's taking that theory and putting it into practice. And one of those things that they often find out is that they've got to get an Allen key or a screwdriver in to actually do a bolt up. And that's things you don't learn just by doing it on a computer. We do see a diverse array of platforms coming through. The things we're going to show, we're going to flick through a load of photos or kind of talk through a few projects we've kind of recently dealt with. But most of those will be fixed wing designs, but we do also see a fair set of VTOLs and multi-rotors designs as well. And we give them a autopilot system to implement in there. And that has allowed the teams to kind of go through a rapid progression to seeing some mission autonomy, whereas before we would see much more kind of RC aircraft style designs. Now we're actually seeing the thoughts going into making it be able to achieve mission autonomy.
So here's some examples of other GDPs that we'll briefly talk about. So we have a blown flap aircraft on the left. So essentially it's a big EDF, and this sucks in airflow through ducts that is inside of the aircraft and for augmented lift on takeoff. So they can now look at the data between the EDF turned on and turned off and make comparisons there. And then on the right, we have a precise aid delivery aircraft. So the idea is a large aircraft could drop many of these and it's going to deliver aid to a specific location. This team went for a tail sitter design and it worked really well in the hover. The transition flew around, could do waypoint missions, come back, transition back to its tail sitter configuration for a nice precision landing. This team went above and beyond, and then they went and designed a release mechanism, attached it to this Believer aircraft, and then in quite a shuttle-esque fashion, we have the release there. So the Believer would invert, drop the little payload tail sitter, and then the tail sitter went and flew an auto mission, continued that, came back, landed, whilst the Believer mothership aircraft was put into a loiter or manually landed.
One of the other projects we've started to run year on, year out now is a project called the FASTER project. And the whole point of this one is to try and build up, at least at the moment, an internal competition, but potentially an external competition of trying to get an aircraft to be both efficient and fast. And so the students are tasked to carry a 1 kilo payload and a battery of a specific size, and fly a 20-kilometer route, which is 20 1-kilometer orbits, with the average speed of 10 consecutive orbits being recorded as their maximum speed. So they have to be able to fly fast for 10 kilometers, but also achieve an efficiency or a range of 20 kilometers. And we thoroughly analyze their logs, so we actually pull out every single orbit they do and check that it sticks with the rules. So they've got some constraints about how far out they can be from the prescribed 1 kilometer route. And last year, I don't know if the numbers are that clear on the screen, but last year they managed to achieve an average speed for those 10 kilometers of 43.21 meters per second. That is currently the record. Hopefully next year we'll go faster, and maybe people outside our university will start maybe looking at doing this, and we'll hopefully get some external competition going. Other projects we've seen, which kind of move slightly away from traditional fixed wing, we've seen a project looking to make a winch-lowered droid to do packaged pickup recovery. And so this one tried to implement the 6 degree of freedom motor mixing. Weren't super successful with implementing that, but that was the idea behind it. And so they would use 4 motors to translate their system, their droid, to line up with their camera recognition system, looking at the ArduCopter marker. And then on the right, we have a design brief which was kind of titled to get them to make a person-portable UAV. So they'd have a system where they'd take the catapult and the UAV, be able to carry that around with them, set it up and launch it. And this utilized the kind of ArduPilot launch systems. So it delayed triggering of the servos to release the tail fins, and then also delayed the motor spin up to make sure there's no fouling on the catapult. And again, for another composite image of it taking off, we have this system. And you can see that one of the tail fins is actually deploying a little bit too early on the kind of second in from the left. And that was just, I think, maybe a slight flex in the structure, but it shows that these students were then implementing delays to the ArduPilot system to kind of make full use of it.
So some other aircraft we'll quickly go over. So this top left one, that was meant to be a high endurance aircraft. Though it did suffer from pitch stability, but it did achieve a high endurance, but it was with the help of a tree. So, yeah. And then we've got the top right, that was looking at toroidal propellers, so you can see the toroidal shape there. So they built the aircraft, but then also 3D printed these toroidal propellers and could switch them out for standard propellers and then look at the data that they got. And then the 3 images on the bottom there, that's like a flying lab. So they could change the aspect ratio of the wing, change the dihedral angle. You can see the image on the right, it's got the wingtips compared to the other two, and it could also change its static margin. Students were making use of the Lewis scripting there to change parameters based on the configuration of the aircraft.
And so all those projects is the systems inside, really, and that's where we've started to adapt our kind of autopilot resources. And the purpose is to try and support the students with hardware, guidance, and advice. And so our autopilot resources we've kind of been building over the years are autopilot starter kits, online guidance documents, the live data dashboard we briefly shown earlier, and also in-person advice sessions.
So kits are great because they're common parts to every team, so they can talk to each other and kind of share knowledge in that way. So, so that's quite advantageous. Also, the kits are sponsored by Boeing, so the budget can go towards, well, they don't have to pay for the essentials that are going to have to go into the aircraft. So their budget, or they can budget for their design of their aircraft. And also we find that this kit and the items in it that I'm sure we're all very familiar with, you know, will basically cover any system that they want to build. The only times that we might have to change out the equipment is if they're building something that is quite small and you know, these parts are too large or too heavy.
And by implementing or kind of allowing them to use common components, we then started to create our own online guidance documents to give that common support to those common components. And this kind of acts as the simplified documentation of the questions that most students ask us about configuring the systems we give them. But it always links back to the ArduPilot resources and the Cube pilot docs as well. And it becomes a useful kind of starting point to getting the students to understand the features that are available for the students. The other thing we've started to implement, we spoke briefly about it earlier, is that live data dashboard. And this was to tailor the information that the students would see on a big TV screen at the flight line with information they needed to see to compare it against their predictions, but also to compare about the other teams flying on the same day. And so we would build it so that it did the 3-second averaging based on the altitude, making sure they're not climbing too much or descending too much, and a different flight mode. And that will get shown under the airspeed. We'd give them a bit of information about the wind speed in the map overlay, and also give the live stream of the video so they can see how their gimbal is performing. The application itself is using the WebSockets connection to Mission Planner, and thanks to Peter Hall for pointing that one out that it exists. It was originally on the TCP. And then it's running an Electron app that has an Express server backend, and is then using an Angular framework dashboard at the front. And it became a really useful resource for students to see what was going on their flight day, rather than just watching an aircraft fly around and hoping that somebody was reading out the airspeed correctly. We also give in-person advice sessions to the students, and this is normally tailored around the design of the system, but it's increasingly, as they want to improve the complexity of their system in terms of functionality, it's increasingly going towards more how do we configure the autopilot system. And so we try and promote those tools, such as the web tools and the documentation, for them to kind of get that future independent resolution of their problems.
So kind of challenges that we face from the kind of situation that we're in, where we have lots of teams, let's say, on a flight day. So as an example, radio interference. So every team has those 868 modules. And we have systematic and physical ways to try and make sure that only one team, is powered on at the same time. We also want people to work on the aircraft in the pits as well. So it'd be really good to hear people if you have any, clean, slick solutions. So switch to one live pair and allow for, low power comms to happen in the background, or to think outside the box in some other way. The other thing is the initial setup and documentation. So there's obviously loads of documentation out there, and that's absolutely fantastic. However, we often find that students feel quite overwhelmed with kind of what is out there, and that's why we've kind of tried to slim down the documentation to our own kind of internal wiki, but obviously using what's out there as well. But we don't want to kind of double up on the workload there, so we'd love to have a discussion about that kind of stuff. And then students and gotchas. So this is more from like I guess a safety perspective. We're giving quite complex systems to students. So we're getting students to build really quite complex systems, and we are ultimately responsible for their safety on these flight days. So often we can see weird permutations of parameters that would result in maybe an accident for the aircraft. For example, we had one where a disarm channel or a disarm command was set to the throttle channel. It was only in a high power state that it would disarm the aircraft. It was only because we were taking off from long grass that we could find that out. We didn't know why for a little while, and then we debugged and we found the reason why. So it's not always as simple as checking that they've got the arming checks on, which, believe me, every student turns off. And we also want to know what is missing from graduates. So there's a lot of commercial companies, or people here are dealing with commercial companies and the hiring of people fresh out of university or not university. And what is missing from graduates? What can we tailor our courses to kind of give them the knowledge? How can we improve our teaching?
And finally, we just want to close with kind of saying there are opportunities. So every one of those group design projects has to have a design brief behind it. And us, kind of on the academic side of things, produce quite a few of those. But we also get links to industry and companies to produce design briefs. So if there's anything you'd like to see tested by students, then let us know. We'd love to collaborate. We'd love to kind of work together on some of these ideas. And that also unlocks kind of access to a lot of the university facilities. We've got wind tunnels, anechoic chambers. We've got all sorts of things. And so you could get involved in some of these student projects, and that could lead on to future research for both yourselves and kind of the university. So thank you for listening. Any questions?
What an amazing course. Can I come?
Absolutely.
Do we have any questions for the guys? One from Dan.
Yeah, I echo what Matt said. Like, that'd be great to have these days. Have you investigated the IMechE UAS challenge? Because that seems very similar to some of the stuff you've been doing there.
Yeah, so we used to attend, I think 2016 was maybe the first year, and we attended that several times throughout those years. We kind of dropped off that a little bit. I'm not too sure why. Recently, we started to pick up on going back to that, and hopefully this year we'll get another one going through to the UAS challenge. Yeah, absolutely.
Yes, hi there. I really liked your tail-seater configuration, and I was just wondering, does the front wings also have some form of ailerons?
Yeah, so the has an all-moving canard on that system. So that was doing essentially their elevator control.
Oh, okay, fine. Thank you.
Yeah.
When you guys are doing the flying with various wings or platforms, do you do any of the tuning aspects, or are you generally using the stock tunes?
For all the plane projects, normally it starts off stock tune, and we get about 6 full-day opportunities for students to attend a flight day, and that will cover probably about 7, 8 to 10 teams. So depending on their state of readiness, they have an opportunity to tune on those days, and then they've got 6 opportunities to get it tuned and then get the data they want. So depending on how productive, ready the teams are, depends on the state of the tune. But normally for the planes, start off on the stock tune and potentially tune it. The copters, of course, are slightly different, and they're going to go through the initial tuning setups.
Have you ever seen any disasters from bad tunes?
We have seen a few student projects that do end up in trees and in fields, normally due to kind of the design, the manufacturing of the drone itself, so they haven't quite considered the structural loads in some parts.
Cheers.
Hi. I saw in a few pictures angle of attack or angle of side slip sensors. Is this something you build a lot? We do need more of those in general.
So I think that might have been about the flying lab one you might have seen it in. So on this one at the bottom. So yeah, this team was really impressive in the sense that they took all their aerospace knowledge from their 3 years of their undergraduate to their 4th year, and they made a flying lab that looked at aspect ratio, they looked at airspeed, they looked at angle of attack, side slip, they looked at the CFG position, all in their different flight tests. I think these are just Arduino potentiometers that they've put themselves together and then done their own data logging from. So I can't, and this was a couple of years ago, so I can't comment on the state of that. But we do see students putting together Arduino-based data logging because they want to just do rapid development of something that they are familiar with because they get taught Arduino systems throughout their undergraduate. So yeah.
Okay, another round of applause, please. We're going into our afternoon break now, and we're going to resume at 20 to 4 out on the takeoff and landing pad for Randy Mackay's small aerial photography drone demo. We're about to start Randy's demo, so if anybody does want to see his demo, head out to the takeoff and landing pad now.
We will shortly be resuming APDC 2025.
Yep. You've got the mission visible there? Oops. Okay, great. So you're going to switch it to auto mode and arm it.
So you're in loiter at the moment.
Hmm?
You're in loiter at the moment.
Yeah,
so
that makes sense.
Yeah.
Switch. Yeah. Cool. I'm ready.
Okay, everybody. We can focus in. Time for Randy's small.
No, right now it's a Blue OS demonstration. So you can hear me okay? All right, so we've got a little EDU 450 out there, and it's got, Cube Orange, Blue OS running on a Raspberry Pi. So we don't have live video on this one, but it still shows you, some of the new and interesting things you can do with Blue OS. So we're actually going to try and demonstrate two new features. One of them is going to be high altitude optical flow. So normally optical flow only works within the range of the rangefinder, but with the stabilized camera and the terrain database, it should work. I've tested it up to 100 meters, and we're going to try and reproduce that. Also, on its way back, it's going to come back at about 40 meters high, so quite high up, and hopefully it will use again that same downward-facing camera, this time for precision landing. So there's a target out there with 2 April tags on it, one big one that should work from high altitudes, and then one little one that'll work at lower altitudes. I've actually never tested both these features together, but hopefully it'll work. So if you look at the mission on the screen, it's a very small screen, but basically the mission is take off to 20 meters, then it flies forward about 40 meters or so. It hovers there for 10 seconds. At that point, I'm going to switch it over to using optical flow and maybe turn off the GPS. So you should be able to see the GPS turn off on the screen there. If all goes well, that's really the most dangerous point. If it stays in control and everything, no EKF failsafe, then we will see it proceed up to 100 meters. It'll hang out there for about 20 seconds, and then it'll come back. We will probably get some drift, so you'll see. If I switch it back to GPS, it'll suddenly move. Okay? All right. So Peter Hall, yeah, switch to auto and arm, please. If you got into auto, I could arm it from here. Yeah, is it in auto mode? Oh yeah. I'm just going to pick it up and we can see if it reconnects. Surely it's going to reconnect. Yeah.
I think.
Yeah, connection's pretty dodgy, right?
Yeah. You do it. We've got a tool person.
Let me see if I can.
Switch it to auto now, and then you can just,
Yeah. I would actually like to see the camera pointing down anyway.
That's auto.
Okay, great. Okay.
It's
Crap again?
I'm not really connected.
Yeah, okay.
But obviously,
I've got control here. I think it's okay. Okay, arming and auto. Okay, so it's going to 20 meters and then it should go forward. Okay. Now I'm going to switch it to optical flow. So that's optical flow. Are you connected? All right, so yeah, so now it's just using optical flow and it's climbing up. So I'm going to turn off the GPS as well. So no GPS at all. And it should hang out at 100 meters for about 20 seconds. So no hands, no GPS. Again, you can't see it really.
I haven't been connected for like 30 seconds.
Okay, I'm going to turn back on the GPS, but it's still doing optical flow only. I think it's coming back, maybe.
I'm trying to look you, sorry.
I think it's coming back. What do you think?
There's quite a long delay.
Yeah. So at some point, once it stops or gets too close to us, I'm going to switch it back to GPS. I'm going to switch it back to GPS only, and we can see how much it moves. So it's coming back to 40 meters now. Okay, so pretty soon I'm going to switch it to GPS. Yeah, there it is. It stopped. So here's GPS on. So that's how much it drifted. I don't know if you can see that, but that's how much drift built up. Now it's going to start an RTL. And it's quite high. So now hopefully with the high resolution camera gimbal, it'll be able to see the target and land right on it. Sometimes you can see it do a little jump when the tag is in range. To be honest, I'm not sure it's actually seen the target. Yeah, I don't think it's seen it. Nah. Oh well, 1 out of 2. Thank you very much. Okay. Okay, we just need a couple more minutes to set up the little one, and then we'll do a quick flight with the little one. So give us 5 minutes. Hey, so this is your guy. Let me plug in the... so this is where we need William. William? So what we need to do is... where's the LEDs? Oh, there it is. Good. Yep, that's right. And here's your mode switch here. Change the model. Yeah, that's roll.
Yeah, roll.
Throttle.
Yep.
Throttle up. Yeah. Change the. Connect it to cockpit and see the video. Is that possible? Because it's got LTE modem, right? The IP address. Yeah. Sorry. Yep. We have Wi-Fi here, I think. Yeah, hotspot tethering is on, so you should have internet. And yeah, we can do 0 here. So, yeah. Let's see if it makes a noise. It does work. That's so weird. It's bound to both. The same. That's working.
So what's the mode switch?
This is the mode switch here. So that, I believe it's stabilized, held, hold, and loiter. And this, turn the fan on. This is RTL.
Yep.
Did I do anything else? I don't think I did anything else. Oh, browser. I usually use Chrome. Sorry. Normally. Sorry. Sorry to put you on the spot. Here's a couple of them.
Yeah, it's the one on fire. Yes,
This one, eh? So here, I'll let you do it. Sorry, you go ahead. Okay. See the flight mode, which would be nice. So I did actually put an auto mission. I think I even set up a switch to switch it into auto. So you could, but you know.
Well, you could.
Yeah. Way over time, eh? Well, we could just maybe.
Yeah, I guess you can take off already.
That's fine. And we could also do this. We could do the UDPCL. Is that it? That looks like it, right?
Yes, that's it. Can I start real quick? Nope.
Yeah, no GPS. Oh, there it is. Good. It's got GPS. Yeah, it'll work. And there is a mode as well. Try. I think it might be this one is auto. No, that's.
Yeah.
Sorry, how about this one?
No, just yeah. So that's.
No, this one. No.
Well, you know what?
Maybe. No, I don't know. Maybe we'll just do it from here.
Yeah, just do it from there. All right. Waiting for home.
Just do this. Maybe it's too late. Maybe we should just.
Just do a little hover and.
Yeah.
Show people.
Yeah, it's not.
GPS?
Yeah, we do have GPS, so it should work.
Well,
all right.
Maybe I'm gonna...
See if you can arm it and loiter. Can you arm it and loiter?
Well, I'm gonna stabilize.
Well, how about loiter? Let's make sure it actually, because it looks like it's not arming. Like you can't. It probably doesn't have a GPS fix.
Yeah. It's...
You know, I don't know. Yeah, it doesn't have a. Well, if we're out of time, we're out of time. So.
What's your guess?
It's a Here 4.
We had a bunch of weird issues with BVLOS GPS.
Yeah, it's only got 10 satellites. Oh well. Okay.
You can force that and stabilize if you like. I mean.
Oh yeah, he can arm it and stabilize. All right. Okay, well maybe just if you can fly it around. Yeah, no, the satellite count is really low. Maybe just.
How long since it was powered up?
Yeah, long.
Fully powered up.
Yeah,
well, that might be
that'll
why
do it.
it's still
Sorry.
doing
Yeah.
it. So it's a cold lock.
Yeah. How do you feel about flying it in alt-hold and stabilized?
Stabilized fine.
Yeah.
I'm more comfortable flying and stabilized to start
Okay.
off with an unchewed aircraft than alt-hold anyway. So.
Okay, great. All right. All right. So, yeah, we're going to do a quick flight. I was going to do, we're running out of time and we don't have quite enough GPS satellites. So we're just going to do a little manual flight, nothing special, just to show you that it actually flies. So Leonard's going to fly it for us. So thank you, Leonard. Is it okay? Or is that alt-hold?
Yeah. Fine, that's my flying.
Yeah. Okay. Anyway,
Yeah.
you've told them, you've shown them that it flies, so.
Yeah. Have we got satellites yet?
I don't know. Do we have any satellites or anything? Okay. Can't connect?
No, it's lost. Still thinks it's disarmed.
Yeah, okay. All right. Anyway, that's it. That's basically it. Thank you very much. Thank you very much. Cool. Great. Thank you very much, Leonard. Yeah.
Oh, well done.
Okay, cool. Great. Thanks so much.
No, I was getting it tuned up better, I'm sure, but
Yeah.
yeah, that was actually quite nice to fly.
Great. Great.
Okay, ladies and gentlemen, please make your way to your seats. Please make your way to your seats. So our next talk is from Dr. Amilcar, who's going to talk about his Ardupilot Methodic Configurator.
Hello, everybody. So I'm Amilcar Lucas. I'm based in Germany, and I've been contributing to the Ardupilot project since 2011. In the last 18 months, I started a new little project called Ardupilot Methodic Configurator. So on this talk, I will first focus why that software exists, what does it do, how does it do it, is it reliable, is it compliant, and how to use it. In the end, there will be a small demo. So, why does it exist in the first place? So Ardupilot is very flexible, as you all know, and it supports right now 266 different Ardupilot boards. So I'm not talking about AP per if. AP per if, then it goes up to 300, but Ardupilot boards alone, 266. Hundreds of different sensors and all the flexibility that we all know it has. So in order to work properly, of course, all of these parameters need to be correctly configured and tuned. So the flexibility is there, but you have to know how to use it. And I've read over, I think, 128,000 posts on the forum in the past few years that I've been active. And I see a recurrent theme from our users asking, okay, how do I configure that? And should I configure this before configuring the other one? And what's the sequence and all that stuff? And it comes because we do have extensive documentation. There's over 1,600 unique pages. I know I wrote an engine to crawl them all, and there are 1,600 unique pages on our wiki. So it requires users to learn a lot and use different tools, and they lose their way once they start reading the wiki. They veer off to one direction, then to another direction. There's no start to finish. So in the end, what happens is a lot of users end up incorrectly configuring their vehicles and coming to the forums and complaining about it, and some of them just don't come to the forums, just go to other firmwares and other stuff. So that's why the configurator got created, to try to address exactly these pain points. So here are some other problems that the configurator addresses. Missed mandatory configuration steps. There are steps that you need to do, and people just ignore those. Because they're overwhelmed or they want to get their vehicles just flying as fast as possible. Then they do weird stuff like auto-tune before notch filter and mat fit before the current sensor is calibrated, and then they go on and calibrate the current sensor, but now the Mach fit doesn't work. Yeah, all kinds of those things. Then we have weird stuff that's been historically there. So if you're trying to configure an ESC, well, there are parameters to configure the ESC under the prefix ESC, under the prefix serial. Some of them are under the prefix mod. Some of them are under the prefix servo, and others from the prefix can. So you're trying to configure an ESC, but you have to look at all these other prefixes. So a parameter tree, parameter name tree, it's not going to get you there, because you do look at all the parameters starting with something, but you have to change parameters all over the place. So, when you're doing a configuration step, sometimes if you're using a tool like GCS, it does present you the parameters, but it doesn't present you the documentation on how to do the ESC configuration, or what is the specific documentation for your flight controller, because we support 266. They care about those. They care about the ones that they have connected right now. So there's some stuff in there that could be improved. And when you're reviewing a configuration or when you're doing a configuration, there's no way on current ECSs, in current ways, to write down why you're changing that parameter. Okay? Today I'm changing the parameter because I did a flight test and I got that and that result. So that a couple of months later, when I go back to it, I get to see why I did that change. So, here's a comparison between generic ECSs, so I have placed in there mission planner, queue ground control, but pretty much any other DCS will behave like that, mission proxy, MAF proxy and stuff in the configurator. So the first point is extremely important. It's probably the most important point of all of them, okay? Full automatic configuration. Can you do a one button push configure of a vehicle like Ardupilot? No, you cannot do it, not with Mission Planner and not with a configurator. So the configurator is not a solution, you press a button, it's done. That's not the point, okay? But it does have other things, like it allows you to do a semi-automated configuration because it's a wizard-like interface, and you have to do step 1 before you can do step 2, and you have to do step 2 before you can do the step 3. So it guides you to that configuration step. Explains you what to do, explains you when to do something, because there's a specific order. You cannot do specific steps before you do other ones and other ways around. So you have to do it in a specific way. The documentation, the same thing. So the parameter documentation, if I'm looking for, I'm doing a motor calibration, for instance, or a motor test on Mission Planner, then I don't have a way to see exactly what motor spin mean is, because the documentation for motor spin mean is actually in the full parameter list, and that's another screen. So the whole thing is not available in a single place, all the information in a single place. Document why you change each parameter. It's something that you also want to do. And it does automatically install Lua scripts. So users struggle sometimes to put a Lua script on a flight controller. And this one just says, okay, and now it's time to do MacFit. Do you want to place the figure 8 script on the flight controller? And you just say yes, it downloads the flight script from the internet, uploads it to the flight controller, that's it. You only pressed one button, you get all these operations automated. The other thing is, every time you configure flight controller to the configurator, it downloads the entire parameter sets and does a backup on your file system. So you always have a backup before you use the configurator, because that's the very first thing that the configurator does. And every single time that you plug a flight controller and you start the software, the configurator creates a new backup file for you. So how does it do its job? It's a wizard-like interface. It starts by checking for software updates. If there's a new software version, you're asked if you want to update. Then it connects to the flight controller. Then ask you to create a new project or open an existing one if you already have one. Then you define the components that your vehicle has, and then you do the parameters. We'll take a look at this later in more detail. So the parameter configuration steps, there's different categories and different things that you can do. So in green, the first one is optional, so you can skip that. if you don't need that, but it has to be done in the very first place because you need to put the FC in the freezer, and if you have assembled your FC onto your vehicle, now you have to put the entire vehicle in the freezer. That's not very feasible. So you should do that before you even put the FC on your vehicle. So that's why it's on the very top, and that's the very first thing. Then you need to assemble all components except the propellers, it's obvious. And then there's the basic mandatory configuration. You have to configure every single device driver. You cannot tune an unconfigured vehicle. There's many users, beginners, that try to do that. They try to go to auto-tune before even configuring their GPS. Don't look at me like that. It happens. So, then you have the minimalistic mandatory tuning that you have to do. But after that you can fly. It's enough for a lot of users. And the software allows you to jump and skip all the other steps, because these are also optionals, and go directly to the last step, everyday use, where you disable logging and do a couple of other things. And that's it. So basically, for beginners and users that don't need a maximum performance, you just follow the steps, jump to the end, you're done. Now, if you want a little bit more performance, do one of these. If you want a little bit more, do a next one. So the idea is that the more steps you do, the more performance you get, but the first steps give you the more bang for the buck. How are the configuration steps structured? So there's two kinds of configuration steps. Simple ones that don't require experimental data gathering. They're just one configuration step. You configure your GPS and you're done. That's an example. And there are others that require experimental data gathering. So they're divided at least in two steps. The first step, you set up the experiment. You configure the parameters that are required to gather the data and perform the experiment. Then you go and fly, and after you've flown, after you've done something like a web filter tool, you come back and you feed it back to the tool, and the tool reads the data from the flight controller again and continues. So it's basically divided into multiple steps when you have to do an experiment. So one of the advantages of the software is that in a single view, so the user can see the parameter default values. He gets access to the tuning guide, so a document explaining which step to do, and it's linear from top to bottom. The parameter documentation used by the firmware version that they have on their FC, not the latest one, but the one that they have on their FC. The parameter limits, so the mean and max recommended limits, the current flight controller parameter values on the flight controller, the connections, so they get to see if their GPS is connected to GPS 1 or GPS 2 and all that stuff. The vehicle component specifications, how big are the props? So there are some components that are very important for the configuration and tuning, and that is also there. The wiki documentation, so links to the relevant page for the wiki documentation. So if I'm doing a notch filter, I get a link to the notch filter page. If I'm doing something else, I get a link to something else. So they get to see the documentation. It's there and it's good, but they get to see it step by step, and they only see the documentation that's relevant for the step that they are currently at. So they don't need to go and read 1,600 pages. So they need to only read those that are presented to them. And if they are required to use a web tool, then that web tool gets opened automatically in the background for them. So it pops up a browser window with the excellent web tools that we have, if that's relevant for this step. So if they're doing the notch filter calibration, then they are first required to set up the notch filter, go perform the flight, and after performing the flight, the web tool opens automatically in their Firefox or Chrome or whatever, and they don't need to go and look up where is the web tool. They don't need to go and look up the URL for that. So is it reliable? Well, it has been used in a lot of vehicles, We have been growing our user base in the last 18 months, and we have used it on vehicles from 600 grams to 350 kilos. All of them use the same sequence. So that same sequence of steps can be adapted to all of these things, and it does work. So it's meant for beginners to advanced users, all of them, same sequence, big and small vehicles. It has currently 1,644 regression tests, and currently almost no known bugs. So is it compliant? So how is the software built? Well, the user interface, it's a little bit old because it's TK Inter and it's not the newest and shiniest, but it uses the paradigm, what you see is what gets changed. So if I have 5 parameters on that list, the tool will only change those 5 parameters. The tool will not go behind your back and change some other parameter. It only changes the little parameters that are relevant for that step. That's one thing. It has been translated into 5 different languages: German, Italian, Chinese, Japanese, and Portuguese. It has no menus, visible or hidden, no menus whatsoever. From the code quality perspective, PEP 8 follows PEP 8 coding style guides, PEP 484 type hints, and all that annoying, boring stuff. It has logging with 5 different logging levels, so from debug to info, critical, fatal, and all that stuff. Follows semantic versioning, and the change log is also, the commits are all following that semantic versioning thing that allows you to classify what kinds of commits are there, so you can see clearly what are the bug fixes, what are not. It's linted with 4 different linters, so PyLint, MyPy, Rough, and PyWrite. It has pre-commit hooks, CI/CD. It has 30 different CI/CD workflows. It has 6 automated robots doing commits and merge requests, like Renovate and Dependabot and that stuff. Now, for the audience on this room, this is probably the most important slide. So, how is it built? What's in the background? Well, AMC, it's just a Python engine, okay? But what it's doing is reading all the information that it needs from JSON files. So there's a JSON file to explain the components on your vehicle. There's a JSON file to explain how these components are grouped in a vehicle. There are JSON files to define the configuration steps that you want. So currently, there's an ArduCopter.json, and that's the one that I maintain, and that's the one that works. And then there's a Arduplane.json that currently it's just a copy of the other one. I'm waiting for somebody, I hope on this room, to help a bit and try to bring that Arduplane.json into shape and get those steps, those configuration steps, to from start to finish to configure a plane properly. The same thing for other vehicles. And then, parallel to the JSON files, you can have an MD file. That's basically the documentation. So, and there's links between those. So the MD file has links to the JSON, and the JSON has links to the MD. So by providing those things, we can add support for newer vehicles like Sub or Heli or whatever. And even if somebody really, really wants and gives a JSON file for a PX4, this thing could configure PX4 because it's basically just talking Mavlink and MavFTP, and that's it. So you don't need to know Python to change the software or adapt the software. If you want to add a configuration step, you just need to do a little change in the JSON file and do a little change in the MD file for the documentation. So this is about the customization. Customization without changing the source code, because everything is data-driven on those JSON files. The vehicle components, the components themselves, and the configuration sequence. All of these things, they have a JSON file and a schema for the JSON. So if you want to validate the data, the software validates that with the schema, but you get to see also the schema for the JSON file. Now the roadmap, what's planned in the future? So in the near future, we plan to do this little addition because currently it's the biggest pain point of our users to get the ESCs correctly configured. And sometimes they need to change the frame type. So instead of telling them, okay, you need to read the documentation and find out what's your frame type, they get a nice little picture of it, courtesy of Yuri. And they can use the drop down there to select what's their frame type. They also get warnings if the voltage is not correct. So if they try to spin up the motors without a battery, the software will tell them, sorry, you have to put voltage on this thing, otherwise the motors will not turn. And they can run the motors. Once they run the motors, they tell which orders the motors are, and then the software goes in behind and sets the correct servo functions for the, okay? So that's one thing in motor test. Then there's status messages. Currently, we don't show status messages anywhere. Automate downloads of the last log bin file. That's very useful because right now to download a bin file, what I do is I use mavftp and log into the board, list all the files, and get the last file. So instead of doing that, I'll have a button that does that for me, automates that, goes there, gets the last file, puts it on your hard disk, so you can use any analysis tool for that without leaving the tool. Simplify and automate the S configuration we have with BD shot is a hairy monster, so you have to set the masks right, you have to set all kinds of weird things, and most people don't get that right, but I'm pretty sure that we can do that with a lot less parameters and in a more user-friendly way. So, and lots of people ask me to make it closer to Betaflight, make it as easy to use as the Betaflight configurator. Well, that's hard to do on a software as complex as Ardupilot, but that's something that I will try to do. I'll try to make it easier and easier for the users to use this and to get their vehicles running. But it's going to take a while, and I hope that some of you get inspired to help me out on this journey because it's hard to get all the vehicles right. And I'm focusing only on copter because that's the ones that I have, that's the ones that I use, and I really need the help on the other ones. And last, automate, and then automate some more. So I'm a big fan of automation, and if it's automatable, I prefer to do it automated than to tell the users, okay, click there, then go there, then do the other stuff. So this thing has a configuration guide, has a user manual, has use cases. So for different use cases, documented how to use the software, where to click, and all that stuff. The software architecture is also documented. There's a YouTube channel with a couple of videos. I'll add some more in the future, but there's some of them. And there's an Ardupilot trained AI chatbot that we've trained with the entire contents of the wiki. So the 1,600 pages of the wiki, they have been indexed by this AI chatbot. And then the configuration guide, the user manual, and whatever, all the documentation from The Ardupilot Methodic configurator have also been thrown in there. I also thrown in there the documentation from QPilot, their entire documentation base. I think CUAV on Olibro also got indexed. So, and all the YouTube videos on Ardupilot channel, the ones that have subtitles are also indexed in that chatbot. So you can take a look at it now so that you get an idea. So this is the, sorry. No, I cannot do that. Not that easy. But if you go to the website of the Methodic configurator, there's a little icon on the bottom right side, and that's the AI chatbot that you can click, you can ask questions. It has all this documentation, and we'll try to answer them for you. So, it's my firm belief that this will reduce the human error probability while configuring a vehicle, increases the configuration speed. You don't need to switch tools and click a lot of buttons. Increases the consistency and the reproducibility. You can have multiple vehicles, and it's like a checklist. So if you have to do 10 vehicles, you have the checklist to go for all those 10 vehicles. And it has documentation and traceability, because for every single parameter, you can add that information in there. So now let's switch to the, how much time do I have? 5 minutes? All right. So let's try to do a quick demo. Somebody happens to know the shortcut to mirror the screen? Yes, it's Windows. All right, cool. Windows print screen? Okay. Nope. It's really weird now. Mm-hmm. Thank you. That was it. So when you start the configurator, it allows you to define the vehicle components of your vehicle. And this is the interface for the beginners. So you can define where you have connected your receiver and what protocol it uses. Then where you have connected your telemetry and what protocol it uses. Same thing for battery monitor. Then you configure your battery voltages and number of cells, capacity. For DSC, again, you configure what kind of connection it has and the protocol. And for the motors, you tell them the number of poles. For the propellers, you tell them the diameter inches. And then for the receiver, again, the connection, how it is connected to your FC. And once you've done all that, you just can save data and start the configuration. But I will now switch to the normal mode. that has a little bit more details and show you how you can compose a vehicle. So if you happen to have some frame, okay, I have some frames here already predefined. You can enter all the data for a frame, and once you've entered all the data for that frame here, manufacturer, model, and all that stuff, you can just click the plus button and it will save that as a template so that later on you get that same data by just clicking here. And you can select for the RC controller, select which RC controller you have from a list. You can do the same thing for the transmitter, receiver. So every single one has these templates, and that saves you time if you're creating vehicles. Okay, and once you've done that, you can go to the next step, and that's the GUI for it. So on the very top, there's a bar where you can see where you are in the configuration process. Some of these things are painted in black. Those are mandatory things. If they're grayed out, they're optional, so you can skip them. As you can see, there's lots of steps here that are optional. Then there's the documentation for every single step. So right now we are on step number 5. And you get to see the documentation for that particular step. You also get to see on mouse over why you're doing this step and why you're doing it right now, why you're not doing before and why you're not doing late. Why is the remote controller done in step number 5 and not on step number 50, okay, basically. It also tells you if it's mandatory or not, and it will automatically open the documentation in browser if you click this button here. So the first time it connects, it detected that it has a Q+, so it will open on the browser, it will open the documentation for the Q+. Then for every single parameter, you get to see if they have their default value or not a normal value. So if something has a default value, it will be marked in light blue. If you change that from a default value to something else, then it's marked in white. And then there's that little symbol between those two things that tell you, okay, if I upload this parameter to the flight controller, then I will change the parameter on the flight controller. And then the main part of it all is this field here. That's the reason why you change this. So in this case, the arming rudder, usually we disable that. We prefer on our drones to use the switch. So I will say here, because we prefer to use a switch, okay? And that gets documented so that a future worker, co-worker, or me in 12 months remembers why is that parameter being set to that particular value and not something else, okay? So, and once all that is done, I can just upload the selected parameters, and it will save this small parameter file into the hard drive, and it will upload everything to the cube. Then it will download everything from the cube because we have a problem on our parameter protocol, Mavlink parameter protocol. ACKs are basically ignored. Sometimes you set a parameter, it does not get set correctly. So, and there's no way of finding out that the parameter has not been correctly set. So we download everything, then we upload everything, we check if they're okay or not, and if they're not okay, we'll upload again. So that saves trouble for a lot of users that sometimes think they've set the parameter, but they haven't because something went wrong, and the GCSs don't tell them that it's gone wrong because there's no way of doing that because there's a fault in the Mavlink protocol. I already talked to Peter Barker about that, by the way, and we'll maybe try to fix that. Let's see. So once all that is done, it then switches to the next step and presents you the documentation of the next step. And the documentation for the next step is to configure the telemetry. So my job right now is to read this documentation. It also opened some other documentation here on our wiki, opened the documentation for the telemetry landing page. My job again is to read this documentation And that's it. So now that I've read the documentation, I should be able to set these 4 parameters. So, and that's what we're trying to ask our users here to do. It's not like, look, you have 1,200 parameters, set them all. What I'm telling the users to do is, right now, concentrate on the telemetry, and once that is done, once you read the documentation for the parameter, for the telemetry parameters and set them, you're done. You can go to the next parameter, but you don't need to read the entire documentation. All right, that's it. Thank you very much.
Thank you very much, Amilcar. I'm very sorry we haven't got any time for questions right now, but if you can follow up with Amilcar if you do have any questions or comments or want to support all the work he's been doing. Thank you very much.
Thank you.
Okay, next up we're going straight on to Bill Geyer, who's going to talk about plane system ID. If you give us one moment. There's Bill. You ready, Bill?
I am. Can you hear me?
Okay, over to you.
All right, thank you. Good afternoon. So my name is Bill Geyer. I'm the Tread Heli maintainer, and you're probably wondering why I'm giving a brief on plane and quad plane. It's all because of the system ID work and analytic tune work that I've been doing over the past year and a half. And so it's wanted to get this conveyed into plane and quad plane so those folks can take advantage of it as well. First of all, big thanks to Peter Barker and Tridge. Peter for gathering some data and going out with his Bixler shown there to grab some data for me to show here. All right, so what I'm going to talk about today is how we've implemented System ID into plane and quad plane, how to use it, what a good frequency response characteristics look like for a good tune. I'll briefly talk about theory and hopefully if we have time, do a little bit of a demo. So, the way we've implemented System ID in plane and quad plane is pretty different than how it's done in Copter and Heli. Copter and Heli does it as a flight mode that basically has stabilize underneath of it, and then the chirp is put on top of, into that stabilize mode, but it's based off of stabilize. Whereas in plane and quad plane, it was desired that we go with it as a feature that can be started through an aux function. And so that aux function is 184 for the RC function. So it's designed to run on top of flight modes, both in quad plane and plane. And for quad plane in the VTOL, it's going to be Q stabilize, Q hover, and Q loiter that you can run the System ID feature on top of. For plane and quad plane and fixed wing mode, they are using fly-by-wire alpha, loiter, and I'm going to implement guided and potentially auto mode as well, once we see how well it does, but that's the goal. And based on feedback I got from Peter Barker and Tridge. So plane and quad plane in fixed wing, in the fixed wing flight, it's the System ID feature is only available for pitch and roll. It was felt that yaw wasn't as necessary for the fixed wing flight modes, and so basically that's all we've implemented into. As far as logging, we have VTOL uses the same logging as Copter, so there's no change there, and it helps with the analytic tune feature. And for plane, we've added a special logging message to help capture the needed signals for the pitch and roll tuning. As far as the flight code status, the quad plane System ID feature has been implemented into quad plane for the VTOL mode. Already merged into 4.7 or for master, and we've actually backported it to 4.6, so it's available there as well. For the plane and quad plane and fixed wing, we're nearing completion. I have a few minor changes to make, put the additional modes in for the fixed wing flight, as well as some minor changes to some logging. But ultimately, you know, for plane and quad plane, they use the same library and parameters for the chirp and how it's generated for the frequency sweep. And so those are the parameters there. So the SID axis parameter is kind of how you start things off. That identifies what axis you're going to be doing the chirp in, as well as where you're going to inject that chirp within the flight controls. The magnitude is the amplitude of the oscillation that it's going to make. You have the starting frequency and the stopping frequency. So you want to design those, or well, first of all, magnitude, let me go over that. Like magnitude, really what I've found as far as the input angles, you really don't need anything larger than 5 degrees. You could actually probably go a little lower if you want. 15 degrees is way too high. And you might be saturating things if you have too high of angles put in there. So best to go a little smaller. 5 degrees is a good starting point. If you don't like that, stop the chirp and make it a little lower. For the start and stop frequencies, you know, I've normally used half a hertz is great. The default, I think 15 hertz, maybe 20 at max for the vehicles that I've looked at. Something like Andy Piper small quads, you might have to go to 40, but something like a 600 size heli or larger like quad plane and planes, you probably don't have to go as high. The record length, that can change. That's the SID T rec. The record length of the record could be, you know, 70 seconds is default. You can go lower, maybe 40 seconds, and that's kind of a crucial thing with plane, because when you're flying 15 meters per second or 20 meters per second, you're going to cover a lot of ground in 40 seconds or 70 seconds. So I have ideas on how to mitigate that. That's why in auto mode, that's kind of nice. You could set up auto mode. That's why you're not worried about. You can always recall it, and you can always set it on a straight shot to get the data you need through using that. Fade in and fade out, basically it linearly increases for fade in, a linear increase the amplitude up to the max amplitude, and then fade out linearly decreases it at the end. Fade out, I normally set to like 1 second. Fade in, 5 to 15 seconds is fine. Normally you might want to set it longer if you have lower frequencies and you're seeing that your aircraft's starting to drift a lot and you want to kind of limit the drifting. You can set that fade in to kind of limit that. Here's the laundry list of SID axis options. You can see for the different vehicle types there. You can notice that copter, heli, and quad plane VTOL are the same there for up to the SID axis 13. And then copter and heli include velocity and position controller options, where quad plane does not. And then for quad plane and plane in fixed wing mode, we only have the 2 for each of the roll and pitch axes. So you have the input angle and you have the mixer. And I'll go over these here in the next chart. This is taken straight out of the System ID wiki. And so you can see the control laws for all axes, actually pitch, roll, and yaw here. And so here's the input where the pilot makes the input. Here's like the input shaping and attitude controller here. Then you move into the rate controller, and which is your PID and feed forward D. And then you finally get to the motor mixer and the aircraft, and then you have your control feedback loops. So for the first input angle, with feed forward enable, that's made here. And then I'm showing the same diagram here. I didn't want to show a different diagram, but this is actually the feed forward diagram. It's also made at this point, except you don't have the feed forward. It's disabled for the recovery angle SID axis option. Next, you can put it as an input into the rate controller if you want to do that. And then lastly, you can put it as an input into the mixer. And this is kind of good if you're going to do a system identification of a vehicle model, or maybe you're doing something like a broken loop stability type analysis. For the fixed wing, this is a generic, I took this out of the wiki as well, and this is a generic diagram for the control laws for one axis of the fixed wing aircraft. So pitch or roll, your choice here, but here's where the input angle SID option is. SID axis is here at where the pilot makes its input, and then for the mixer, it's down here right before it goes into the mixer. So, and again, I added this so that you could do system identification of a quad of your airplane, or, and have that data available. All right, so how to use it. So in pre-flight, there's a number of steps you got to go through. First of all, the big thing is that this feature is not built into the standard build for plane or quad plane. So you have to use the custom firmware builder to compile the code and include that system ID feature. Right now, if you go there and you look under the plane category, you'll see system ID support for quad plane. That will probably change in the near future and say system ID just general in the plot, and then that will cover both quad plane and fixed wing. And then you load that on your controller. You modify your SID axis parameter initially. You have to make that input as to what SID axis you're going to use. You write the parameters and then reload the parameters, and then or refresh them, and then you'll be able to get the rest of the settings that you'll be able to make. I guess I would recommend input angle for fixed wing tuning and recovery angle for VTOL. And Andy Piper and I found out that if you have an angle P greater than 10, his was like 24, and it made very large inputs. So so don't use recovery angle if you've got very large angle P's. Use the input angle instead. And then another key feature or key thing here to mention is for plane, the schedule loop rate is actually 50 hertz by default. And so I would recommend you change that to 100 hertz so that the minimum logging is at 100 hertz. And I would recommend you just keep it there, because once you do your analytic tune, you don't want to degrade your loop rate to 50 hertz again when you've tuned it with the loop rate at 100 hertz. And then what that feeds into is that the log bit mask sets that logging rate, and it's a combination of fast attitude and medium attitude. If you want it at the full loop rate for your logging, then you'd have checked both fast attitude and medium attitude. I think that's the best way to go. Just check those. It's more data is better, and I don't think you have a problem with running out of space. Set RC function to system ID number 184, and then put it on a switch so that you can invoke it from your controller. All right, how to use it in flight. So you'll take off, climb to a safe height. If you're using quad plane in a VTOL mode, it's just like multi-rotor or heli, where you're just going to hold a constant height. You'll be in loiter, Q loiter, Q stabilize. I can't remember the other one. Q hover, and you'll implement that. For plane and quad plane and fixed wing flight, you really need to, so it's important to hold a constant height and a constant speed. And the reason for that is because there's scaling that occurs. And I believe the parameters like A speed, or the variable is A speed, that's used. And then there's an airspeed conversion, that's the EAS to TAS, which I think is kind of a conversion from of the pedostatics to true airspeed. And so that you definitely need to have those constant, because I have to average those over the run. And if they're not constant, then that could affect the quality of the analytic tune you're going to try to do. You'll enable the system ID feature through the aux function. So once you're up there and you're steady and ready to go, you'll flip the switch, and you can see over here to the right, you'll see that it starts doing the oscillations. This one's done in pitch. And you'll notice that for plane, kind of a big feature here is I have this in loiter, and I've set a fairly large radius to the loiter so that the aircraft roll angle isn't much greater than 10 degrees. I found that you could probably get away with around 10 degrees roll attitude for a pitch frequency sweep, and even for a roll frequency sweep, so that it kind of keeps it in orbit above you and closer to you. But again, that all depends on speed, right? That angle has to get larger if you're going faster speeds. the radius to maintain 10 degrees would have to get larger as you have faster speeds. Once your chirp is complete, you'll either be told through your ground control station, or if you just set a timer and then stop it after, or flip your switch off after the timer ends, then you'll be done. Big thing here, right? Must have a stable initial tune. If you see that the aircraft starts to go, with high oscillations, then you want to stop the system ID and then try to figure out what's going on, get a better tune. You're probably got some instability that you're exciting. Quick frequency to time domain to frequency domain, because if we get to analytic tune, we need that for that discussion. So in analytic tune, we talk about two things: gain and phase across a number of frequencies. So the gain is the output amplitude to the input amplitude, as shown over here for a constant frequency oscillation. So there's my output amplitude B, input amplitude A. I do the ratio of those two, and that gives me my amplitude ratio. I could do that in decibels. It's just a conversion that's done there. And then the phase describes kind of the comparison of the peaks in time for a given frequency. And so kind of in most cases, you're going to see that the peak oscillation input will occur after, or the output will occur after the input, as shown here. And that take that time, and since it's a constant frequency, then we can determine what that phase is. And so that leads you to the Bode plot, which then shows the gain or the amplitude ratio as a function of frequency and the phase as a function of frequency. The goal here is, when tuning, is to make sure that your output is equal to your input, which for decibels is 0, so it's a 1-to-1 output to input. And then, as with anything, like if you were to drive your car, you've noticed with your aircraft, as you make higher frequencies inputs, you'll see that the aircraft does not respond as quickly or does not respond as much as amplitude. And that's what basically this is showing. As you go up in frequency, the amplitude starts to drop off of the output, and the phase starts to get worse, that it starts falling behind the actual input of the input signal. So what defines a good tune? This is Peter's data for the pixeler in the pitch axis. And so you can see this is the calculated frequency response for attitude. So we want the actual attitudes to match closely to desired attitudes, meaning that you want this to run at the 0 dB as high as frequency as possible. Good disturbance rejection, little to no overshoots. That means that you don't want this to bump up above 0 dB. Otherwise, that means you got more output than you have input. And then you want the response to remain in phase with the desired input. So basically, you want 0 phase as far out as you can. And so I did a little playing in analytic tune, and this is what I found with some settings. I was able to get it to stay to 0 dB all the way out to about 3 hertz. And I was able to keep better in phase out to maybe 0.7 hertz. Real quick about theory. So this is analytic tune, basically takes and looks at, determines the bare airframe dynamics, and then analytically wraps around the control loops. And so based on linear system theory, and essentially if you have any rate or acceleration limits, that'll affect linearity. If you have anything like slew limiting and it's actually being invoked while the frequency sweep is going on, then that will also cause problems, and you won't have a good comparison between the input, the calculated, and the actual predicted. And so real quick, I'll just jump over and just show a quick, here's the tool. This version's not up there yet, but basically you could choose your data. Once you choose your data, you then, you have your start and stop time. You can modify that, but really you're just going to choose the sit axis run that you did. So he did 2 of them. One was roll angle and one was pitch angle. I'm just going to choose pitch. Come on. And then I'll go ahead, and you have to hit calculate down here to get it to do the analysis, and then that puts out the comparison. So the big thing to do once you start this is initially with your settings, when you first get into it, you just want to make sure that the prediction matches the calculated pretty closely out to when you start seeing a low coherence. When this gets below 0.6, then you have low coherence, and you're going to expect that the output won't closely match the input. So that's really the litmus test initially, and then you can start making changes to your gains up here to then change the response and what it looks like. So I lowered this guy a little bit. I think I lowered this guy some, and then I definitely lowered this a lot. And then when I go to attitude, the attitude plot you can see there now matches the gain is around 0 dB. I think that's all I have time for. I guess I'll stop there and take any questions if there's any questions.
Hi. Are there any plans to also backport this to Ardupilot 4.6 once you are done with the Arduplane, 4.6?
I guess that would be up to Tridge, but I don't know if we will. I think we'd probably wait until 4.7 comes out, but I'd probably push that to Tridge to answer that question.
Okay, and are the results like you get from a 4.7 like test usable in 4.6?
Yeah, I would imagine that the results would be acceptable because I don't believe there's any large changes to the control law structure between 4.7 and 4.6, or there probably won't be.
Great, thanks.
Mm-hmm.
Okay, thank you very much, Bill. One more round of applause, please.
Thanks, everybody.
And that brings us to the end of our day. So if I could kindly ask everybody to exit and get onto the buses, they will take everybody to La Piazza for the conference dinner. Thank you very much.
Thank you for joining us for the Ardupilot Developers Conference 2025. With thanks to our sponsors, 3DXR, Aerosystems West, CUAV, CubePilot, High-Tech, Holybro, IR-Lock, KH Unmanned, Kraus Hamdani Aerospace, Maytech, Modal AI, Northwest Blue, SD Model, and Theseus. Organised by KH Unmanned. Hosted by 3DXR in North Yorkshire. Broadcast by Cube Ranch.